FDP is ongoing. So my presentation will be based on the fact that before getting into AI or IoT for a building to, like, let's say, make a digital twin, it is important to understand how the structure behaves in a seismic condition, etc. You might be able to understand there are many avenues in which your AI and IoT can actually help in, let's say, disaster mitigation to actually post disaster reconnaissance. Like once the earthquake has happened, how can you check whether a building is suitable enough or not? There, your AI and IoT can help. Or the performance during an earthquake, or even before, has to do a health monitoring kind of a thing through a digital twin. It is all possible. So to understand where to use it, it is necessary to understand how the structure behaves. So before the structure, this particular thing is related to earthquake. So we understand that the earthquake can happen due to, let's say, tectonic motion. We know that volcanic eruption or man-made activities. That is how an earthquake can occur. Now, when an earthquake occurs, you have to understand that it is due to the ground motion vibration, and it can impart on the structure acceleration, velocity, and displacement, etc. And due to different intensities of earthquakes or due to different magnitudes of earthquake, the damage that is there in the building can be varying. Now, when you ask me ki earthquake ke liye, I mean, civil students or civil faculty might be able to understand that yes, during an earthquake, we expect damage to happen in the structure because we are taking care of the forces through the use of response friction factor. What we do is, if an earthquake is going to come and there is a demand, let's say 1,000 kilonewton demand as such, think of it as a force right now. We actually divide that force by a certain number, based on which, what is it based on? It is based on the ductility of the system. The more ductile the system, the higher value of response attraction factor we use. So we expect that when the earthquake happens, it is not going to be elastic, the entire structure. It is going to deform, it is going into the inelastic range. And then because of that inelasticity, there is going to be bound to be some cracks that is going to happen. Let's say it is hinges in the columns, cracks in the walls, etc. That is going to happen. The main intention of design of earthquake design is that the philosophy with which IS 1893 and the different codes with which your buildings are made is with the intention that if there is a severe earthquake, the structure will not collapse and your life is safe. So that is the case that we expect damage to happen in the buildings, right? This is the latest seismic zoning map of India, wherein you can see zone 2, 3, 4, 5, and 6, where zone 6 represents a very high seismic region, right? There is a high seismic region that is there, and you have high to very low. So you can see the upper Himalayan belt, the Bhuj area, the Gujarat area where we had the 2001 Bhuj earthquake. Then we have the Andaman Nicobar and a little bit of Latur region where we had an earlier earthquake. That are the highest seismic zones in India. And you can see one more thing, that there is no place immune to earthquake in India. Somewhere or the other, there is a kind of it can be key, an earthquake can happen in these regions, right? So this is the latest seismic zoning map, which is based upon the probabilistic seismic hazard analysis. So this can't be better than, there is nothing better than this in terms of understanding the seismic zoning of this thing. Now, if you want to understand how the building responds in terms of an earthquake, what happens is simply like how a teacher would explain, like, okay, earthquake is something like the forces is in the ground, like the ground motion is happening. So why does the buildings attract these forces? Is because of the inertia. So the mass of the building. If you're standing in a bus, the bus moves forward, you are pushed towards it backward because of the inertia. Same way, if the ground motion is from left to right, if the ground moves from left to right, your building sways from right to left. So that will create some kind of stresses. Let's say any material, if I bend it, there will be some stresses that is developed. If the stresses are within the elastic limit, the building will come back to its original position. If it is more than that, it will go into the nonlinearity. So how is the force transferred? The slab where your furniture, where your tiles, where your live load, where your load itself is there, that is a main contributor of inertia in a building. And your walls, columns, and everything are the ones which resist this kind of forces that comes into the thing. So how is the force flow? From the slab to the wall to the footing, or from the slab to the beam, from beam to the column, and column to the foundation. That is how the force transfers happen, right? Now you need to understand one thing, that the building can move in any way, right? I mean, if an earthquake comes, you are not saying that the earthquake will come from left to right, top to bottom. It can come in an angular fashion also with respect to the building. But the building has, you have to understand that as in nature, everything has a natural frequency. The building also has a set of frequencies, which you can call as a natural frequencies. So how will the building move is an important matter in terms of an earthquake design, is that we design the building in such a way that the preferable way the building should move should be in a translatory fashion, which means my columns are like right now rectangle, like a square you can see here. So it has two principal direction, one in this axis and one in this axis. So ideally we would want a translatory movement to happen in these things. Like it should not go in a, even when in whichever direction the earthquake will come, the principal frequency or the primary frequencies of the system should be moving it in the translatory way, like either left side or towards the up and down for this particular geometry that I have shown you, right? With that understanding, what does happen in a normal building? In a normal building, you will have many changes, right? If you can see this building, it has a heavy side, means you can think of it as like your structure. You may think of the building that you're sitting now. You have a water tank on the top. You may have a heavy kind of a what do you say, a heavy weight kept there, or a library at the top of the floor, or a gymnasium on top of the floor. On one side of the building itself, that will induce some kind of a torsion. That is what is being shown here. Now, when we expect a translatory motion, if such kind of a mass is kind of heavy on the right side, the overall structural behavior will show a kind of twisting movement, which is like inducing torsion in it. Torsion is not kind of preferable in terms of a building. So what does the code say? Or there are design codes that are available in India, which says that okay, you make sure that once you design the building, you make sure that your first two modes in the terms, first two frequencies relate to a translatory motion in the building, and the torsional mode should be shifted towards the backside. Which means if an earthquake comes, the primary mode will be translatory and the torsion should be avoided. But if at all, let's say you cannot do away with your building design, right? You may be placing your water tank towards the right side, towards a corner of a building where the toilets might be there, etc. If you're doing that, then you have to add some stiffer element. Let's say it is twisting like this. What you have to do, either you have to stiffen this particular area such that its center of, I mean, the key plan here is to ensure that your center of gravity of the mass and the center of stiffness with respect to all the elements, let's say walls, columns, etc., are lying at one single point. Both of them coincide. If both of them coincide, that is center of mass and center of stiffness, then there will not be any kind of torsion. So we have to take care of such kind of action in the building behavior. Now, if you follow that particular kind of a nature of how the building should behave, if you follow the code, etc., we believe that in India we will not be facing any kind of failures or anything like that, right? But as I said before, in for a building, if you are doing IoT or AI kind of a study, there are many avenues where you can work it. One is post earthquake reconnaissance. Let's say an earthquake happens in a particular area, the building may be behaving in XYZ way. Maybe the first mode is torsion, maybe the first mode is translatory. There are cracks that occur in a particular building. There is like plastic hinging, means non-linearity has like completely come into a beam or a column. It is necessary for you to understand how to identify what has happened, right? So what the case is, let's say I visit a site after an earthquake, or if I go to a building after an earthquake and see certain cracks are there. How do you identify what the building has what has happened to the building is very crucial to understand. So the buildings, even when we say these are regular buildings, code defined buildings, we know that the architect and the user usually controls what to be made. You yourself will say, I need car parking in the bottom floor, I need the floors to be above. So you are inducing some kind of irregularities in the building. An irregular building, I am calling it irregular in the terms that you are manipulating the code in such a way to kind of have a kind of beneficial kind of effect for your functionality, but it is violating the codal requirement with respect to these things that we have discussed so far. The ideal behavior that we want, we may be violating. So what has happened to such buildings in previous earthquake is what I'm showing. The key here is I will be showing the types of failures that the building has experienced. But you have to understand from an IoT AI kind of point of view is that every type of irregularity will lead to a certain type of failure. The idea is whether you are doing post-earthquake reconnaissance or whether you are doing digital twin kind of monitoring, certain areas or certain locations are vulnerable. You have to understand beforehand itself where the vulnerabilities are, so that when you say digital twin, you are putting some sensors or something like that. If you're putting the sensor at the wrong location, you might not get the idea of what is happening, right? That is the idea that I want to convey. You need to know how the structure may behave due to a certain irregularity, so you provide the sensors at the right location to get the right idea. Or post earthquake, you go to a location and you identify whether you're flying a drone around the building or anything. You have to identify what failure has happened. So this is a soft story failure. What do you mean by a soft story failure? Is that this is because at the ground floor level you have stiffness being very less. Mostly that happens when you have parking on the ground floor or when you have shops at the ground floor, let's say like this. So what happens is that at the bottom floor there are only columns, maybe walls. There are no infill or partition walls there. And on the top floor you have the normal buildings like this. There you have partition walls with bricks, etc. So what happens at the lower floor is a lower stiffness, and on the upper floors you have a very high stiffness. So what happens when the earthquake comes? It has a vulnerability at the lower floor. So this building was actually a three-story building, and it failed at the bottom floor, and the bottom floor is totally now absent. In this particular building you have an intermediate floor. People will have some kind of a open kind of an atrium or something like prepared, so that has caused this kind of a failure. This is another type of failure that you see similar to soft story failure. This is another soft story failure where you have one part of the building like actually collapsed, like it has a parking on the bottom floor, right? What are the other failures? There can be floating columns also. You have to look at the structural diagram of the building to first identify. The first thing that you should do with respect to whether you're placing a sensor or whether you're flying a drone, etc., is to understand what might be the structural configuration of the building. There may be a column which starts from the top, but it does not follow to the bottom to transfer the forces. Then it is a problem that at this level there will be a higher concentration of forces that may develop, right? That can cause failure here. Else, if your column was beginning from the bottom and was stopping at here, that is fine, because you have a continuity till the foundation. The forces from this floor will be flowing till here. That is not an issue. Floating columns are floating in air. That you have to understand. Like it is not continuous and it is not transferring the forces from its bottom side to the foundation in a direct manner. It is going in an indirect manner, that it has to flow from here to the cantilever beam. It will be flowing like this. That will create some problem. Like this, these are examples where such kind of things was looked at. You can see this is a simple example, right? If I have a plot size of this much only, what I will do as a tenant or a building owner, I will try to increase my floor area on the upper floors, and that will cause a cantilever here. Again, this is a discontinuity. I'm not continuing the column to the bottom. That has caused a shear failure in these beams at this location. And after the earthquake, people have kept temporary columns at the end of it to kind of give a support to this particular location so that the building does not collapse after an earthquake. So you have to understand what the vulnerabilities are. And for such buildings, you have to place sensors accordingly. This is another with mass irregularity. There is a penthouse at the top. There may be a larger foot area at the bottom, which is like a podium area where more shops will be there. So suddenly you have kind of stress concentration at this location, as well as a mass irregularity at the top where the masses are very high, like a water tank here. You can see how it has got damaged during the earthquake. Next is pounding of buildings, which is like two buildings which are side by side. Gap is very less. That is how we build nowadays, that each plot are side by side, so there is no area between them. When an earthquake happens, more than the structure getting damaged due to any irregularity here, it is damaged due to the pounding between the two buildings which are nearby. If the slabs are on the same level, let's say slab on the left side building and the right side building are on the same level, damage will be little bit less, because slabs in its own plane is more stiff than out of plane. Whereas if the slab at one floor is different than the other, you have more forces hitting it and going accordingly. So in such type of a building, you have to understand how much drift or deformation the building is going to undergo. Accordingly, you will place your instrumentation accordingly. Now, when we say earthquake, we normally say if an earthquake happens, what should you do? Normally, what we do is we run from the building. We say, okay, run away to a open place and stand there. But the most vulnerable kind of a locations are the staircases. Why they are vulnerable in the sense is that when a design engineer designs these kind of staircase, he does not consider staircase modeling in totality, like a diagonal element going from one floor to the other To consider the loads, he applies a simple plain load on the top of one particular floor to consider the loads that is going to come to the column. But if you think in your mind that the slab, the staircase slab is like moving from two floors with a landing in the middle, where is the landing forces going and attaching to at the middle of the column? If you don't design the columns properly, if the columns are going to fail and the slab is, I mean, the staircase is going to come down. So what is the best thing to do during an earthquake? Is not to run away from your building. The better thing is to hide below any kind of a bench or a table. That is the better way. If the building survives, you survive. Then we have another problem. If you are looking, if you are saying that, okay, I understand how the building is going to behave, these are the vulnerabilities, these are the issues that I have. The next vulnerability that I have is the reinforcement bars are corroding. People are not using the correct kind of reinforcement bar, or they are not using the right type of water, which is like drinkable water to use it. There may be chlorides in the water, etc., which may cause corrosion to the rebar. What happens during corrosion is that your thickness of the rebar will go away. If you are in a building right now, if you look around, if you see cracks in your beams or columns running parallel to the rebar, it is due to corrosion. It is nothing due to structural deficiency or any strength loss or anything. It is only due to corrosion if you see a crack running parallel to the rebar. Now, if you have a rebar like this, in which the thickness has gone due to corrosion, the thing is that your structural capacity has already depreciated with respect to its overall, the higher value that it already had, or the value with which it was designed for. So these issues you have to monitor that where is that deficiency. I mean, normally in an area where water is there, whether air is there, that is a place where the corrosion can come. Else you have poor quality of material that is being used. Sometimes you don't find I mean, the right cover which needs to be provided. So if you are thinking like, I can digitally monitor the condition of a structure, you have to understand where and all it is going to deteriorate and why and all it is going to deteriorate. That you have to understand. Then let's say you have won the battle with respect to the code, you have understood how the building will behave, you have understood the material can go wrong, how it behave. You have one more person who's going to alter what you think about the building, that is a contractor, who is going to do such a thing that there is no shear reinforcement. If you see a building with, let's say, a column something, you will see when it is being built, you have vertical reinforcement as well as you have transverse reinforcement, something like this. The function of transverse reinforcement, yes, it is to take care of the shear. It is to take care of giving buckling resistance to these vertical rebar. Those are the functions that a shear reinforcement is there to do. And it is also there to kind of give confinement to the concrete, because it increases that confinement due to that horizontal stirrup is going to be there. That is going to increase the confinement strength of the concrete inside that particular cage. So it has three functions. As I said, it is to resist the shear strength, to give extra strength to the concrete within this. And the third one is to avoid this kind of buckling. Because as soon as an earthquake happens, there is going to be peeling off of the cover concrete. And if there is no stirrup there, it is simply just simple bars standing. So there is a huge possibility that they will buckle under the compressive forces due to the self-weight of the building or due to the earthquake that is going to happen. So if such an arrangement is already there in your building and you are thinking that it will behave like an ideal manner, no, it will not. So if you don't have the ideal mechanism or the kind of sensors, I'm again and again saying sensors, but you can think it of as a way of mean of identifying what will happen to this building. If you don't identify what is going to happen, it will give you a very wrong message that everything is okay. So every irregularity, building irregularity, being having torsional or heavy mass or bad material or bad workmanship or execution, can all lead to a different answer if you don't consider it properly. Yeah, then you have masonry wall failure. You have this infill wall, right? Brick wall, which is kept for partition. It is not there for carrying any load, let's say in a column frame arrangement, column beam arrangement. Once this falls off, let's say you have a sensor which measures what is the time period of the structure, right? Natural frequency of the structure. During an earthquake, what can happen? This wall can fall off. What will that happen? What will that lead to? Reduction in the inertial forces. The self-weight of the building will reduce. So now you will say, okay, sir, inertia has reduced, so my structure will behave good. But then you have some stiffness irregularity also coming into picture. So building in every stage of how it gets damaged during an earthquake can throw a different surprise to you. So you need to have adequate measures to kind of identify that why that has happened. You may be sitting in a room, sitting with your computer model, etc. Suddenly there is an earthquake that happens, and this wall falls off. Suddenly it will show there is a reduction in time period, right? If you come to the site, you will understand that if I make a infill wall once again, its time period is restored, let's say, for the time being. But if you sit at office, you will say suddenly the structure has, has lost lot of weight, which means it might have collapsed. It might have some other kind of interpretation you have to do in terms of saying that why that time period has elongated. Because of mass loss, it is there. Why the mass loss has happened? Maybe the building has collapsed, or maybe some floor has dropped off, or something like that, right? So you understand how it behaves. What is the next? You have different materials coming into picture. It is not just nowadays that you have the RCC elements with concrete poured and kept. Trying to save time, people are using these precast panels. They say quality is maintained. You are doing it in a very fabrication yard or a casting yard. You're making it so quality is good, and it saves times by just bringing it to site and placing it. But during an earthquake, such kind of precast panels are the ones which is like strict no in terms of in a high seismic region. Precast systems are not allowed because they don't have an integral behavior. So systems also, like the way you try to bring it together, the system can also have a different problem. Now again, your plot size, let's say it has a corner, like your building is an L-shaped or a irregularity, plan irregularity is there. Like from top, if you see, this is an L-shaped building. What happens? This arm moves left to right. Let's say this arm moves front to back. What will that cause? It will cause high stress concentration of the corner of the building, right? These are the issues that if you go to a building, let's say you're going to put a sensor or anything like that, you have to understand that such kind of a thing, like at these corners are where the stressors are going to concentrate. That is where the damage is going to happen maximum, and that may lead to the failure of the building. This is an old 1964 image, Alaska earthquake, that at the corners you have major damage. Rest of the building there is no damage. So that such kind of concentration happens due to these re-entrant corners, or kind of a something like this. So these are the plan irregularities. You can say nowadays that architects are being more ambitious. They are making too many irregular buildings just to make the building look nice, but then that has an implication on the overall behavior of the structure. You might say, okay, why don't we put a leash on their thought process, that why can't we make it uniform like this? So code actually gives the direction that how to plan the building, how to ensure that torsion doesn't come. So these are all the checks that are already given in the code. Torsion irregularity code, irregularity check, then re-entrant corner, how much projection, how much L is good, how much of a projection in one direction is good, the code is already giving you. So if it is a code abiding building, yes, its behavior will be different. If it is not code abiding, you may find such kind of a failures that you saw earlier, like this, like this. At the corners, you can see the damage. There is a crack, whole crack here. I mean, after the earthquake, the point comes out that the whenever the authorities come, the point is, can we reoccupy it? The first question. Second question, how much will be the cost of repairing this? So if you already have made the building vulnerable, then the cost is going to increase more, right? Next is you have these kind of explanation that is already given with respect to the code as when will a penthouse at the top lead to a mass irregularity. The code already says that, okay, if the mass on one particular floor is more than 150% of the floor below, then it will lead to a problem for your building. So if you use that, there are already directions given by the code. Let's say vertical geometrical irregularity, these kind of buildings are there. In New Delhi, in Chennai, in different places, these kind of structures are already there. So such kind of structures already have a defined. I mean, people have made this earthquake has come and attacked them. They have a certain kind of behavior problem that has been observed in it. So based on that, these kind of issues have already been observed in such kind of a building, right? Again, torsional irregularity is there. You can see center of stiffness as well as CG of the building are at different locations, leading to torsional irregularity. So the code says how to check them and how to avoid the problem. If you don't do that, these are the kind of failures that you see, which is the Alaska earthquake, 2001, and then Mexico City, 1985. These are all buildings which were affected by torsion, etc. Then you have openings, like in malls and all. When you go to a mall, there is a huge opening that is given to have an atrium opening, something like that. But That leads to the diaphragm, the whole floor panel becoming very flexible, which means if the floor plan is very flexible, it will throw more forces to columns or a certain part of the floor rather than moving it uniformly in one direction. So these are all the issues that can come. So what is the takeaway from this thing is that, okay, in a good seismic resistant structure, you need selection of the load resisting system, configuration system, basic dynamic characteristics you need to understand, and construction quality should be the best way in order to kind of get the ideal behavior from it. But if you're into IoT and AI for a building or something like that, what you have to understand is you have to understand the dynamics of the structure. What you have to understand, you have to understand mode shapes. Mode shape in the sense how it's going to move during an earthquake. What is the fundamental frequency? What are the natural frequency? Whether it is going to twist, whether it is going to translate, etc. You have to understand. Then you have to understand the building frequency and ground period. Why I have put both as similar to a building having a natural frequency or a pendulum having a natural frequency. The ground is also having a natural frequency. So what do you think if the ground natural period and the building natural period is going to match? You're going to get resonance. So your building damage is going to increase more. So it is not just enough to look at just at the building. There should be some understanding about what is a time period. So sensors with respect to understanding the time period of the soil, or not sensors but assessment of even time period of the soil below the structure is also important before you move on to the structure. That is a point that I want to convey. So if you don't know about the soil and suddenly you are saying something is failing, you don't even understand what is the issue, you will be in trouble in kind of interpreting what has happened. Damping, if you increase damping in a structure by any means, what will happen? When it translates, it will come back to rest very quickly, right? If the damping is more. So higher the damping, the better the structural performance is going to be. Normally, in a building without any kind of normal RCC building or a steel building, normally this damping is around 2 to 5%. Nothing more than that. But if you add some damping devices, let's say a viscous damper, like you have in a bike, right? Shock absorber kind of a thing, if you add, the kind of damping that comes into the building goes up to 30%. So people add that kind of a damping. Let's say wind, it's not just for earthquake, but even for wind, people use viscous dampers. I mean, viscous dampers are normally known to be used to resist wind, like tall buildings in Delhi, etc., where we have wind forces coming in. People are complaining about vibrations. They are not able to sit in their house because of these vibrations due to wind, simple wind, not even heavy wind during a summer season or something like that. So you use damping devices to increase the damping in the structure such that your translation is reduced. That results in reduced damage in your buildings. Ductility, as I said before, in a building, ductility is the most important characteristics. The higher the ductility, the better the performance of the structure is going to be. The lesser the ductility, yes, if you are ready to pump in more money, you want no damage in your structure. Now that is the new way in which people are going, is that why do you want to put sensors, is to kind of check that a new system you have devised, let's say in a hospital, you don't want damage, right? The same concept that you're using for a house, where you're saying that when I design for earthquake, it should not collapse and kill the people. You cannot have the same concept for a design of a hospital building, which you want to have, I mean, to be operational after an earthquake also. So ductility there becomes a different notion. But yes, ductility is the most important requirement, and in an RCC building, that is normally provided by the reinforcement bar that you use. Seismic weight, yes, the higher the weight of the building, the higher the inertia, the more the seismic forces are going to be. So try to use lightweight materials. So you have to understand, when you go to a building, what is the partition wall made of, whether it is brick wall, whether it is solid wall, whether it is AAC blocks. AAC blocks are now in trend in terms of lightweightness and things like that. The behavior with respect to that infill panel is also important. If you have a simple frame as a beam and column, its behavior will be different when you have an infill panel inside it. It becomes more stiff, right? If you have an infill wall touching the beams and columns, when it is moving or swaying left to right, it adds stiffness, more stiffness to the structure. The more stiff, the time period reduces. The time period reduces, the force in the structure system increases due to earthquake forces. So everything has a correlation. So you have to understand the dynamic characteristics of the behavior of the structure. Then only you will be able to predict what is going to happen, or deduce from what has happened to understand what is the damage or anything like that. Then redundancy. The more the columns, the more the transfer elements that you have. Like if you have more number of columns to transfer the inertial forces to the foundation, the better it is. Then non-structural elements, as we talked about infill wall, that is there. Foundation, you must have seen normally for your normal buildings, it is isolated footing. It's like a square footing. Then you have raft that is entirely covering the entire building. If your soil is not strong, it is like a weak soil. Then if it is a very weak soil, you go for pile foundation and everything. So you have different foundational system, and that has different fixity. I mean, every building is not fixed to the ground, right? The ground, it is just inserted into the ground, and based on the foundation system and the soil behavior, the amount of fixity. The building which is shallow, having a shallow foundation might sway more than the one which is having a very rigid kind of a footing or a very deep footing in a soft soil. So you have to understand the behavior. So soil structure interaction becomes also a problem for you to understand how it behaves. Otherwise, you may predict the time period is X, that the value that you get from your analysis or IoT or any devices is some other value. And I mean, you may spend years and years on trying to look for the problem in the building, but the problem might be entirely in the ground, the way it is anchored to the soil, etc. So you have to understand that. And foundation soil is again to understand that the ground motion is not a simple vibration that starts from the focus. I mean, you understand that when there is a tectonic motion, there is a release of energy. That energy may be 25 kilometers below the ground, and that too some 100 kilometers away. This event has happened. The vibrations start from there and reach your site. Through when it travels, the original vibrations or the kind of amplitude and frequency that that motion has is not the same that comes to the building. It has different kind of amplification that can happen. So if your building is on a soft soil, right? If your building is, let's say, on a hard rock soil, it's on a mountainous area and vibrations are coming, the vibration will not amplify. It will be just the same. But if it is in a soft soil, it gets amplified more. So you might be assessing for a different number, but actually it may be amplified. So the amplification characteristics of the soil below the building is also an important characteristic to understand finally how the building is going to behave. So if you are thinking of making a digital twin, if you are making to do a post earthquake reconnaissance, you have to necessarily understand everything that is written here in order to finally get the ideal what is the behavior that you're going to get. I hope this is clear now. Now, if I look at a steel building, let's say you are encountering in your work with respect to this particular kind of a objective, that whether this is a steel building, let's say this is a beam, steel beam, this is a column, this is an RCC beam, and then this is the RCC column. The ideal behavior, let's say in a moment resisting frame in India, if it is an RCC frame or a steel, mostly popularly it is a moment frame. In moment frame, as a structural engineer, we would ideally want this kind of a hinge forming during an earthquake. Now, as I said before, this is the ideal behavior. I mean, during an earthquake, we expect damage. This is the plastic hinge. If civil engineering faculties are here, this is what a plastic hinge looks like in an RCC frame, where you have yielding of the rebar at the top and bottom, you have the plastification over the entire depth, etc. And in a steel, this is the plastic hinge formation at this location, right? So when you use strong column weak beam criteria, I mean, you must have heard about these criteria coming into picture. That criteria was not meant for the fact that if I, as a structural engineer for an earthquake domain, make the strong column weak beam criteria, that is, make the beam weaker than the column, such that the beam fails, you have enough time to escape, but if the column fails, the entire structure may fall off. But you have to understand that the actual reason why strong column weak beam criteria has come into the code is to have adequate hinges, plastic hinges forming in the beam, such that you can dissipate the energy coming from the earthquake. That is the main reason that is there. You can understand that if I consider the other way around, if I have a weak column, strong beam means I need only 1, 2, 3, 4, 5, 6, 7, 8 hinges forming, and the building can actually collapse, right? Due to soft story. When a soft story happens, hinges form at the top and bottom. I need only 8 hinges. When this becomes destabilized, and the whole structure can fall off. But if I do strong column weak beam, which means the beam is weak, due to higher bending moments at the ends of these beams, etc., the hinging will form here. Look at how many hinges can form, which means these many hinges, inelastic hinges, where the material is going to go into these inelastic kind of a thing, inelastic behavior, to dissipate whatever that extra amount of energy that is going to come. So this is the ideal behavior that we want. But as said earlier, due to the inefficiency of the architect, the structural engineer, the material provider, the contractor, etc., we might not ideally get this kind of a behavior from the structure. But you will provide an ideal when you understand that this is what I want, and this is, let's say the drawings are all good, the detailing is all good, the material is all good, the soil is all good, you will be providing your strain gauges or accelerometers in locations like these. Like if you want to provide whether the material has yielded or not, you will provide your strain gauges at this location, right? If you understand the ideal behavior, you will provide it here, not here. If you provide it here, you will always see that the material has not yielded at all, but the time period has suddenly shifted in your another sensor. So you're totally confused and sitting and kind of saying that what has happened, right? If you understand the ideal behavior, then ideal behavior only comes when you follow everything to the T. If you're not following, then according to what I've said, let's say there is a parking at the bottom floor and there is a tendency that soft story can happen. Where will you place your maximum sensors? You would place at the top and bottom of the columns at the bottom floor, right? That's what I want to convey, that if you have soft story, you will provide your sensors mostly here to understand whether the hinging is happening, etc., something is it occupiable, how much yielding has happened, etc., you need to know here. But if it is totally designed, placing at the column and not placing in the beam will send you a different signal. And while making this plastic hinge, you can see the area under the curve. When these red dots are formed like these, you have the cyclic motion. During earthquake, this beam is going to go top, up, down, right? It is going to have a cyclic motion. This is called as a hysteresis curve, and the maximum area inside the hysteresis curve determines how good that energy dissipating system is. If you have equal energy dissipation in tension and compression, you are dissipating more energy, the better is there for the building. So now look at what is the hysteresis curve for an RCC beam column joint. You look, the area is not good enough, right? Why? There, I mean, there's a pinching. This is called as a pinching effect, which is like this graph is pinched in the middle. Why that happens is because of this concrete getting crushed or kind of deteriorate or damaged during this particular cyclic motion. So you have decrease in area, so amount of energy during the middle phase when it is coming down to the initial location is very less. So you can understand from this itself is that the steel structural system is much better than the RCC kind in terms of its behavior. But in India, yes, majority of structures are masonry. Then whatever commercial or new structures are coming up, whether we are making our own new house, it is coming normally in RCC. So why are we not going for structural steel in a high seismic region? The cost of structural steel is very high. But if you look at the overall behavior or the life cycle cost with respect to if some corrosion happens in rebar, I may not know until the concrete falls off. But structural steel is a better system, but due to cost of it, it is not currently into use. Apart from moment resisting frame, which is like a column beam, there are other structural systems also. You might have seen shear walls in around the periphery of the core area of let's say a lift or a staircase kind of a thing. Its behavior is totally different from this. Here the overall behavior is like flexure in beams and columns. The shear wall, as that term suggests, that it is like a shear kind of a system wherein you have ductile reinforcement provided to kind of give you a better reason. Then people use dual systems also. You may mostly encounter structural system like these in your area, where the core wall or the staircases are mostly shear wall, and then you have RC moment frame going alongside it. The behavior of this is totally different from this and this. So you have to understand the structural system and then go ahead accordingly. Now the question is, okay, these are all Bhuj earthquake images that I have shown you, some Alaska, some Mexico, etc. Now the question is, yeah, the topic was with respect to resilience. Now, does building a good design, building a structure with good design and everything ensure your resilience? Actually, you can see this example that I brought forward is 2011 Christchurch earthquake. Like in 2011 in Christchurch, New Zealand, there was an earthquake which is like a 6.3, 7.1 kind of an earthquake. And what you see here is the central building district zone, which is where the entire their what you say commercial capital, like what we have Bombay, it is mini Bombay for them there. And what happened was that before this particular earthquake, the structures there were RCC and masonry, and after earthquake, it is like they have shifted to steel structures. Now the point of showing here is not to kind of show that steel structures are good or anything. The thing is that, okay, post 2011 earthquake, the ratio of buildings with the steel, RCC, and timber lateral force resisting system is now 79 in steel, 20 in RCC, and only 1 in kind of masonry or timber kind of a construction. And mostly, yes, the cost of steel is less. In terms of steel chart, you can see by 2016 the prices are less there. And then this is a kind of, I mean, the advantage for them was steel prices went down, and then whatever steel structures were already there were showed better behavior. This is an EBF system, eccentrically braced frame system made in structural steel, which is like damaged during the earthquake, but after earthquake, the same system, they didn't replace everything. They cut the beam here, cut the beam here, they cut the braces here and replaced it with a new one. So why am I showing this is to show the resilience in terms of that. Okay, this is that business zone in 2011 before earthquake. This is after earthquake. 3 days after earthquake, you can see some patches. You're not able to recognize that whether it is damaged or whether it is collapsed from the plan. But after like 14 months, you can see what has happened. You can see a clear area of many buildings getting wiped off from that particular location and new buildings coming up. Like till 2020 also, people were kind of constructing buildings in this particular area at the locations where earlier there was another building. So the resilience is like, okay, I have my economic activity, I have my social activity, I have my functionality of that particular area being normal. The earthquake event happens, there is a dip in that activity, that economy has suddenly fallen off, economy has gone down, the social activity has gone down, and the resilience is about how quick can you get back onto the original phase of the this thing. Now for them it is like 8 years, let's say 7 to 8 years, to get back to where they were originally with respect to building construction, etc. You think of our country in terms of very congested areas in your locality. If such an earthquake happens, we already know that the buildings are not designed appropriately, because maybe for a low rise 3 story where we make our own home, we don't have a designer, we don't have to kind of get it approved by a structural engineer or anything like that. So the resilience comes in terms of that, okay, you might encounter, I mean, uh, this is an older case that in India we are not going into resilience or anything, but the new India, maybe after Bhuj earthquake, etc., Bhuj earthquake, but recently, I mean, after Bhuj there was some devices and all were being used, but now it is being used rampantly. One, the reason is because people are more aware. Two, there is a new code IS 1893 part 1 and everything that has come in, which has increased the seismic forces, the diagram that I've shown you with respect to that. So when you go to a new building, people will call you, let's say IoT or something like that. They don't want this to happen to their area or their building. So they might call you to say that, okay, I want better functionality from my building. I don't want my building to collapse during an earthquake. I don't want even damage to happen in my building after an earthquake. So can you put your devices and tell me when my building needs a repair, when my building needs actual kind of has damaged or etc. You need to understand that newer systems are coming in. So yes, you are into IoT and AI, you need to know what are the new systems that are coming into picture, that you are not a kind of newbie to this area, that okay, what are these, you need not say. MRF system is the same moment resisting frame system, which is the beams and which are the columns, etc. out there. CBF system you might have seen in industrial buildings in India, etc. We have seen, but normally in industrial building it is used to resist wind loads. But now these are used in buildings also to resist seismic forces also. I'll tell you how it behaves, etc. This is buckling restraint braces, again a kind of higher, better version of CBF, concentrically braced frames. Then there is EBF. The difference between CBF and EBF is that it is not concentric, like there is an eccentricity. You can see where my cursor is, there is a link element, there's a short length of the beam, which is like having, which is not where the brace comes and meets. Like here, the center line meets at one location for both the braces. But here in this, you have a very small length of the beam, which is like eccentric to where the center line of the braces meet. Then there is steel rocking system, and then there is yield resistance, which is like the friction dampers. So these are all devices, as I said before, which increases damping to the system. This is conventional, that is okay, but you can understand if you look at the new code, etc. It is clearly mentioned that beyond 15 meters, this is not good in a high seismic region. Why? Because in a moment resisting frame, it is not stiff enough, right? If you have a moment frame system, you know that it is going to sway, it is going to deflect. But if I put a diagonal brace here, it is going to stiffen the system. So my deflections are less. So when you design a building, obviously the limit state of strength as well as limit state of serviceability comes into picture. Normally, we are more worried about the strength criteria. But in terms of a structural system like moment resisting frame, if you go beyond 15 meters, etc., the limit state of serviceability governs the design. The drift is more than what your strength is required. So you need more stiffening system. Unnecessarily, you will increase your beam and column sizes. That's why the system restricts the use of MRF system in high seismic region beyond 15. These are all the systems that are recommended. Now, if you see IS 1893 part 5 that has come in, you can see that EBF system is what is recommended in zone 5, 6, which is the best system out of everything. They say only use EBF system in your these kind of system. And then you have base isolation. You might have seen videos of Japan using this, etc. After 2001 Bhuj earthquake, people have started using base isolations in hospital building kind of a thing. So when you go to a building, check the drawings carefully, check for any kind of rehabilitation or retrofitting that has happened or any kind of changes that has happened. So what happens if you go to a building and you neglect that, you are not looking at the drawing, you keep some sensors, you keep something, the overall behavior is totally different. If an earthquake comes in a building which is base isolated, your top floor is not going to show any kind of relative movement between two floors. It will be kind of a rigid, kind of a solid block on top of it. The more movement will happen at the bottom. Now, a base isolation works in such a way that it increases the time period of the structure to a higher value. As I said before, it is not just the mass of the building, that the inertia of the building that increases the forces in the building. If your structure becomes stiff, it attracts more forces. If it is flexible, it attracts less forces. But the issue with flexible building is that, again, if it's more flexible, it will deflect more. So this is an ingenious way of saying that, okay, I'll not make my building more flexible. What I will do is I will artificially artificially increase the time period. I'll increase the flexibility of the overall structure without increasing any flexibility in the beams or columns. Introduce the base isolation device here. So what it does is the seismic forces, and through this element it introduces the seismic forces rest remaining whatever at let's say that the initial time period of this structure was, let's say, 1 second or 0.5 second. The time period of this structure is nearly 2 seconds or 3 seconds. So the amount of forces has reduced. That is why the deflection or deformation of this particular above the structure is very less, because entire energy is absorbed by this guy. So in such a building, if you keep a sensor at the beam here at the end, like a moment resisting frame, you might not notice anything. You might not notice that it is yielding or anything like that. So structural system or the improvement that has been made or any kind of changes to improve the performance might alter the way it is going to behave. As an example, and as a kind of work that has been done in Roorkee, etc., I'm going to show you with respect to CBF, that is concentrically brace frame, as how it is being used in earthquake, etc. Just as an example, I mean, I've shown EBF as well as BRBF I'm bringing in. So this is like a vertical truss, right? You have a brace frame system. It is like a structure with braces is like a vertical truss. So in a vertical truss, in a brace frame system, this is like a way in which resilience is brought in, is because you have in your household appliances, right? And you have a fuse that is there. So if voltage is very high, the fuse blows off and safeguards your electrical appliances. The same way is the function of these braces. So why Christchurch moved in order to get resilience? They moved from normal RCC to these kind of systems, these new things, is that in this particular structural system like CBF, the as in an electrical system, are these braces. So during earthquake, what happens is these fuses undergo inelastic deformation. So under tension, it yields. Under compression, it buckles. Right? Buckling is not bad in these kind of systems. Buckling in the braces in the brace frame is not an issue. If buckling happens in the column, buckling in the braces is what you want, because in tension, you see, this is again the hysteresis curve that I explained before. The area under the curve is good for you. So you have in that tension area, you have large area that is getting covered, you have large energy that is dissipated. But in the compression side, because of buckling, initial buckling, you have less energy that is dissipated. So it is having an asymmetric. I mean, earlier, if you remember the curve, it had almost equal area in top and bottom, tension and compression. But in this, you have lesser amount of area in the compression side, which means this has some deficiency in terms of dissipating equal energy. So what do you do in a real building? You can't go with only one brace. You provide two braces. So when the earthquake is moving the building from left to right, this becomes in tension, this becomes in compression. So this dissipates more energy. This is like not active. But when the earthquake moves the building right to left, this goes into tension. So after buckling, if the tension comes, the buckled brace will straighten first of all, then go into the elastic zone again, and then it will yield again, and it will go on doing that. So in that way, you need tandem. You need a brother sister standing together in a brace because it has this kind of behavior. Right. So if you are looking in a brace frame system, where will you keep your devices or monitoring devices? On the brace, to understand whether it has yielded or not. It on this particular floor level to understand how much it has drifted. Mostly what happens is when you use these fuse system, whom are you protecting? Like which electrical appliances are you protecting in terms of your beams and columns? You want them to be safeguarded, right? You don't want your businesses to go down. You want resilience in your structure. You want maximum damage to concentrate in these elements so that your beams and columns are safeguarded. That is the whole sense of what is being done here. The EBF system, which we were minutely looking in terms of, you couldn't find what the eccentrically braced frame was, that it is like if you draw a center line from here to here, here to here, there is a small link element at the middle. Now, in these kind of system, who is the fuse element? They are not the braces in these system. The link element is the fuse here. So every structural system, if you go, there are EBF systems in India, there are CBF systems in India. You have to understand the structural behavior, then only you will be able to understand how it is going to behave. So here the link is the guy who is going to yield in shear, let's say. This is a short link. So it is going to yield in shear, deform in shear, and diagonally buckle in shear to kind of use all its energy dissipation capacity. So your sensors mostly should be covered around here. I mean, if you have limitation of sensor, let's say I have one sensor, where to put it? My choice would be this location to understand where it is, right? You have to understand the behavior. Then there is BRBF, right? You have seen this image where this is a brace. You have seen this EBF. Now you understand this link element in the middle. But BRBF look exactly like CBF, right? Orientation configuration is different, but it is still concentric. So what is the difference is that if you have ever learned the buckling of column in your BTech, whether it is computer science student or in your college level also, you must have read about Euler buckling equation, right? It's when does a column buckle when under compression is like pi square E by L square, right? But you have always used an n square pi square. I mean, there is an n square that is coming here. That n square is like if it goes into multiple modes of buckling, like if it goes into higher modes of buckling, that n becomes, let's say, first mode is what we normally say. That is what is most easiest way that it can fail, which normally any member or any structure would use the lowest potential energy to kind of get away with respect to carrying the load. But what if I stop that and allow it to buckle in the higher modes? So I provide a casing around this. So internal there is a core, externally there is a concrete element or something like a restrainer there. When the axial force happens, it axial loads act only in the internal core area, and it applies forces there, and this external restrainer restrains and pushes into higher mode. So what happens in terms of CBF, where you had zero, like almost kind of negligible contribution in the compression area? Look at what is the same CBF when restrained and pushed into higher modes of buckling. You have almost equal contribution from the brace in the compression side also. So this is a much better system in comparison to CBF. In US, Japan, and everyone, BRBF is very popular in terms of giving seismic resilience to the structure. India is picking up. The codal compliance and everything is going to come up. So what is the issue? If you see a particular building, an RCC building in India, mostly building will be RCC. And in that, if you see kind of braces, steel braces, the question will be, can I attach steel braces to an RCC? Will it work? Will it kind of, I mean, am I seeing an architectural element or a structural element? You have to understand that if even if you provide this for a seismic resilience point of view, you have to attach this ideally most efficiently to the RCC element. Let's say I don't attach it, I keep it like this. What is the use of it? It will not transfer any forces or yield or do anything because it will fall off as soon as the earthquake comes. So the first point is how to attach it. So what we did in Roorkee is that currently in Indian code, it doesn't speak. I mean, even in American code, with respect to a beam column joint, let's say this is a beam column joint in an RCC, and this is a brace, whether it is BRB, CBF, it doesn't matter. You have a gusset plate through which it will transfer the forces to these joints. So the ideal point is how to kind of ensure that they get ideally attached to it is through anchors. You can see chemical anchors. You can, I mean, whether your building is already built or whether it is in the construction process. If you look at buildings, let's say after this lecture, you look at your building and you say, yeah, I have a parking in the bottom floor. So maybe my structure is vulnerable to soft story failure. You don't have to worry because there are devices and there are equipments there which can attach a steel brace to your existing RC column. That is to chemical anchors. So you have to drill a hole in your RCC, you pour in chemicals inside it, then you can actually put inside a bolt there and you can test how much force it can take. So this particular study was actually done to understand how much force it can take with reinforcement, everything following the detail what we normally follow in the structural practice. So see, you can see how it behaves. I'll play this video for you. If you can see, this is being pulled. So you must understand that the behavior is totally brittle. The force is increasing. Force is increasing. No physical damage is visible. And suddenly see what happens. I'll play it again. The damage happens in the very end when it is like a brittle, almost like a brittle failure as to what this connection is happening. Initially, nothing happens. And then suddenly it pulls off. So you have anchors getting pulled off from the concrete, chemical anchor. So how do you check the behavior? We did different practices, etc. So you have a diagonal crack, you have edge failure, all these kind of failures is bound to happen in a structure. So what we did is, okay, if I use a 12 mm anchor on versus a 16 mm anchor, the problem that happens is that, okay, the failure pattern is same, but the anchor may fail if you have a lower diameter of anchor rod that you're going to use. So one part of it was IoT and AI. The other part is to increase resilience. So with respect to increasing resilience, yes, you have different devices like CBF, EBF, BRBF, all those things that we discussed. But all of them are useless unless you attach it adequately to your RCC or steel structures. In steel, it is easy to understand because you can weld it, you can bolt it, etc., etc. But if you are attaching it to an RCC member, the issue comes with respect to how will you attach it to an existing one. In a new one, yes, you may inside the reinforcement bar, when you are binding the reinforcement bar, you may give kind of slots or any kind of other kind of devices inside and then cast it. But if you are working on something like, am I doomed if my building is already built without the code and such kind of thing, there the resilience can be increased by using such kind of devices like chemical anchors, etc. That is the point I want to convey, right? So the next is, okay, you have shown it in very small sizes, small scales, etc. Will it work in the actual structure? So what we did in earthquake department is that we casted this 5.1 meter frame. The height of the frame is 5.1 meter. The width is 4.5 meter. You have a plinth beam, you have masonry wall, you have slab on the top, which is like kind of mimicking a kind of real frame, a real size frame. The column beam size is like 230 by 350 mm. The column section, the foundation beam, plinth beam, etc., are of sizes which is representative of what a normal low-rise 3 to 4 story structure is going to happen. And then we casted the whole system. This is the facility at earthquake engineering department, and we applied axial load to it. And in a normal floor, you have axial loads coming into the columns. You have slab, you have columns, you have beams here, and you have plinth beam here. So what do you do? In a normal case, you have to retrofit it or you have to increase the resilience. Means you first drill holes. I mean, this is by attaching CBF, let's say. You attach holes, then you insert chemicals and anchors. These are bolts with chemicals that are available. You can connect with Hilti, you can connect with what do you say, Fisher, those kind of people, they produce chemicals like this. Then what you do is you bring plates, these edge plates with holes already in them. You insert these plates into these where the locations of the bolts are, and then you tighten the bolt. So what you have done is you have made a surface onto which you can attach the gusset plate, etc. Like on the steel plate, now you bring in the gusset plate, you weld the gusset plate here. Now in the gusset plate, you attach the braces to it, right? You can weld, you can put a slot and weld to it. Now, if you have a V type of configuration, which is like your braces, I want to retrofit it, let's say. I want to use a V frame kind of a thing. So what you do in the middle of the beam at the top, this is at the top. If I bring my pointer back, this location right now, what is shown here is this location right here. So if I have a brace like this, moving like a chevron kind of a way, inverted V kind of a thing, I have to drill holes in the middle to kind of get it. So again, the same process, drill hole, insert the chemical, and then insert the bolt, then keep the plate which already had the bolt holes made according to these anchors. Then on top of it, then bolt it, then on top of it, weld the gusset plate. And then epoxy plate bonding. That I'll explain it to you. Additional plates were provided at the sides of the beams itself. I'll explain it to you in the next image. So you see this image, what I had explained earlier. So this is a frame which has been retrofitted, or to increase resilience, such a brace has been added. You can see the gusset plate, the brace, the gusset plate, and then you see additional plates here. So what you have to understand is that it is suddenly when you add a new element to increase the resilience of the structure, let's say adding a brace or anything like that, you may induce additional forces to the existing beams and columns. If I have these braces here, additionally, this part of the beam may be subjected to higher shear forces. Let's say this brace buckles. You have tension in this brace. Suddenly, there is a vertical force that is going to come. This place was not initially designed for a higher shear force, right? Which was coming now due to this particular brace. So to increase the shear capacity of these beams, some local retrofitting should be also done. Only by adding brace is not enough. You have to understand we initially went with a design of a 4-story building, let's say. So initially there is no brace here, there is no plate here. The shear is with respect to the demand coming from the vertical load, dead load, live load, etc. But when you add a brace to add resilience, suddenly you are saying that, okay, this brace will add my resilience to it. It will fail during the earthquake. So whatever it needs to have, let it have. It should not fail early. So what if the RCC beam fails due to shear, there is no use of the brace that is there. If the columns fail due to additional shear that is coming, the provision of brace, if it is there alive without any failure, no use. So everywhere when you kind of think of resilience, only global retrofitting through shear walls, through braces is not enough. Somewhere, some locally, some demand will also come to the beams or columns where such kind of an action as to add maybe a concrete jacketing, an FRP wrapping, or a steel plate jacketing like the way it has been done is needed to improve the behavior. Now, how it is improving the behavior, I'll come to it. You can look at the image of how the testing has been done. You can see these are the braces there. This is the test that is done. It is doing cyclic, which means the frame is being moved left to right. You can see the braces dancing. The fuse, the hero of the element, is dancing now. You can see at this deformation, it has started to yield because this has started to elongate. The area has started to elongate. Right? It is buckling in one direction. It's yielding in the other brace. And you can soon see the brace fracturing, right? Once the brace fractures, there is a sudden drop in the aerial. Sudden drop in the strength value. So I'll play it again, but understand that this is an RCC frame retrofitted with steel. So earlier when I showed beam, which was structural steel, which had a larger area, when you retrofit an RCC with steel, it is still an RCC kind of a behavior there. So it is a mixed behavior that is going to come. But you can see when a brace yields, you can see the yielding to happen like here. Like it is elastic initially, then it is yielding, and then if there is any sudden failure, there will be a drop in the capacity of the brace. So that is what is again going to happen. So you can see once again that when it yields, it will be easier for you to understand when it yields. It has started to yield at around 0.75%, 0.5% drift. The area is going to increase because yielding is increasing furthermore. When it fails, there will be a sudden drop when the brace actually fractures, because then the frame is enough. I mean, then the RCC only comes into picture. Right now it has failed. Now the brace has failed. Right. So this is how you check. Now you can see the damage. So what has happened? In the next image, it will be very clear to you. I'll go this way. Initially, without the brace, the frame was tested. Initially, without the brace, just the frame was tested. You can see where these dots show where the inelasticity initially happens. So 0.3 at percentage drift, it formed at the base of the column here. Then here, then here, then here. If you look at the first row on the top, you can understand that without these braces, this particular frame was undergoing a soft story failure, which is like the hinges were forming mainly in the columns, which is not what we want from the ideal system. But when I put the brace here, you see who is failing first. Who is the hero of the story? The braces. The resilience has increased. Then the beam is yielding. So strong column, weak beam criteria, all those things is happening because I have additionally locally retrofitted this area through these plates, etc. So initially the brace is coming into action, but those extra plates that I added at the corner and the middle is pushing the beam into yielding first, not the column. So here the column actually yielded at 0.3, but even at 0.5% drift, it's only the braces and the beams. So if we go along, it's again braces and the beams, and somewhere at far end only the columns come into action. 0.78, 0.2, 0.3, etc. Only the columns are coming into action. So how does it look after the test with the braces? Is that okay? Can you see any damage in the columns? No cracks, nothing like that is visible, clearly visible in this particular area. But you can see the plinth beam. Normally, as a designer, we don't design the plinth beam adequately. We think that, okay, it is only there to carry the wall load, etc. And because of that only, this damage is happening seen in plinth beam area. Then infill also, due to water ingress or rodents, etc. In India, we construct plinth beam there. So you have damage in this plinth beam area and this area, and major damage in the brace. But you cannot see any kind of cracks or anything like that in the beam or the column area in the frame, and not even in the retrofitted, like this particular area you cannot see. So this is what resilience is all about. And if in a diagrammatic way, this is the bare frame versus this is the, you cannot see a brace here. So this is the bare frame and this is the retrofitted, right? So if you look at the backbone curve, what do you see? If you look at the backbone curve, this is the bare frame kind of a backbone curve. How do I draw? I pick only the peak points in the curve and I draw the peak points here from the bare frame as well as from the retrofitted frame. So if I take the backbone of the bare frame, this is the peak strength it has got. There is a drop in ductility around 50 mm lateral deformation, and there is a drop afterwards. Whereas in the compression side also around 50 mm, there is a drop in the capacity, and then it stables around, it drops to a very low value. But if you look at the retrofitted frame, at that 50 mm, there is no drop. There is a constant strength. I have more ductility in this system, the red color, the retrofitted one, than the other one. So this is the new age of buildings that are coming up, where people are using friction dampers, CBFs, BRBFs in terms of understanding the overall behavior of the system. Whereas in terms of if you look at the older buildings, you need to understand what is the vulnerabilities in them. Because nowadays, if you go, there is a procedure like, okay, you have to vet it from IIT, you have to vet it from NIT, you have to vet it from any academic institution of your building. You have to submit your designs in the municipality, etc., etc. There is some catch. But yes, there are still low-rise household buildings which are made not with code, but simply as that. So if you are going into IoT, AI, or even structural designing or anything like that, you have a what do you say, a menu of buildings, the ones which do not follow the code, which follow the code but are not new, some deficiencies still exist. Then there are new buildings of these kind of nature which follow the code, which have a different behavior during the earthquake. If you don't understand each building, the way it behaves during an earthquake and after an earthquake, it will be very difficult for you to to kind of work around as to how to identify the failures or predict its behavior during an earthquake. So with that, this is our department's facility, etc. Just to for your view. Thank you very much. I am finished in the right time for some questions. Yes, Krishna. If there are any doubts from the participants, then
I have a doubt, sir.
yes, Krishna.
Sir, that steel bracing you told, sir, that which side of the building the bracing has to be done, sir? That is, you show on a picture that it is at the middle of a bay of
Huh.
two. So what if it is in the corner?
It is much better. I mean, if you look at in the sense of understanding, the question is first where to place the braces, right?
Yes.
The thing is that key you can place it in the interior core areas. You can provide at the periphery also.
Uh,
Interior anywhere if you keep it will be a functionality problem as it will not be able to do that. But you can provide it in core areas also. I mean, around the lift where you provide a shear wall, at the exact location you can provide a braces. They function in the same manner. They provide stiffness, they transfer forces, etc. But you understand that if you provide in the periphery, your torsional rigidity of the building increases. So if you have a building whose torsional kind of rigidity is what is mattering to you, you will provide mostly in the periphery. Now the question is whether you in the middle or in the corner. If you remember the torsional rigidity kind of a thing, the farther the distance from the center, the better it is. So the corner becomes the most ideal kind of location where you can give a brace frame in terms of that. The only catch there would be that the corner column, let's say, if you provide a brace here, then you might be providing a brace here. This column will be very heavy. It will look little bit heavy. That is the only thing. Otherwise, on the periphery towards the corner would be the most ideal locations to place the braces. But sometimes you to see here, their steps are there, right? Sometimes a
yes.
person might not want a brace here. That's why, okay, I'm accommodating in the middle of the way. That way.
Uh, the weight of the building also has the matters, sir, in this
Yes,
criteria.
the dynamic characteristics, as I said, overall behavior, like your total building weight is what will transfer the forces to these braces. So if you have a very heavy building, your braces, what you look here, it will be much more thicker, much more kind of stouter than what is seen here. So the more the forces, the brace sizes is going to increase. I mean, more forces comes from more inertia. So heavier the building, more the requirement. You can say that, okay, I don't want to increase the size of the braces, then you have to provide it in more number of bays. To reduce the size of, to accommodate the same force, you have to provide more numbers and more bays. That is the way.
And one more question, sir. If we do anchoring in that, the punching shear may arise due to what we
No,
the boat.
Normally, in a flat slab kind of a system, if you think of or a footing with an isolated footing, punching shear checks and all we do, right? If I do an isolated footing or a raft footing, when there is a column which doesn't have a head or anything, it can punch through the slab or the footing. That is where the punching failure comes in. But in case of anchors, the typical failures are like pull out failure, edge breakout failure, shear failure. In ACI 318, there is a whole chapter on how anchors fail with images, etc. So you can find different there, but punching is not one of them. Normally, if you have tension or you have shear, compression may it doesn't happen much of a problem. So normally, if you are pulling out tension or shear, the anchors may fail. So what you see here, uh, what you saw here is like an edge breakout failure. This one. So you have a pull out failure here. You have edge breakout failure here with the concrete. But if I was supposed to push it, let's say, pushing compression does not induce much of a failure in terms of anchors. It is all tension and shear, which is more critical than compression.
Oh,
And punching normally happens in compression.
okay. So one more question, sir. That is, you showed a drift of 5%, maximum drift of 5%. So
Right.
I have a curiosity to know whether the magnitude of the earthquake at what percentage or what level we have the drift of 5%.
Yeah. Normally, what people do is people do numerical modeling, etc., of structural systems, and then they subject it to DB design basis earthquake as well as maximum considered earthquake levels. which is like when we design for an earthquake which has a return period of once in 475 years, right? And then we have MC level, which is the maximum considered, like in an area like whether it is Roorkee or whether it is Chennai or whether it is Bombay, there is always what is the maximum earthquake that I can expect at that location. So if I consider that earthquake and people have assessed the overall behavior of the structural system, RCC, etc., they have found that this overall behavior is touching 5% or 4% kind of a level. So what people have understood is that okay, if I ensure that if I make my structural system behave good till 5%, then I have got a good system in my hand. Because what happens in a brace frame system after 5% is that the brace may survive, let's say, but the connection pulls off or fails after 5%. Drift is very large, right? I mean, 5% drift is like moving, right? You can say 150 mm is like 4.5% is 150 mm of movement in the structure. When the 150 mm movement happens, the beam column joint is like a kind of a very concentrated area. Your gusset plate might simply peel off or pull out from the concrete. So because of that issue, people have understood that if I have a system which can survive under MC level, they saw that the requirement is 5%. Through, let's say, ETAB model, OpenSeas model, they saw that okay, 5%. In that 5%, which system will survive is the question here. So moment frames, okay, it survives. Brace frame, yes, it survives. So that kind of a way.
Okay.
Yeah.
So participants, if you have any other questions, you can ask now, please.
Sir, I have a question, sir.
Yes, ma'am.
When you're designing for the connections,
Yes,
how do
ma'am.
we give importance, sir?
Which connection, ma'am? In which type of
the steel joint connections.
Okay.
When we are providing for the bracings with the column.
No, the idea basically is what you want to achieve. Let's say I am designing a moment frame system, then I want a strong column, weak beam kind of criteria. So if I have beam capacity to be less than the column, then during an earthquake, as I shown earlier, plastic hinges will form, which means the beam will reach My, which is the yield moment. It will reach its plastic moment capacity. After going beyond My, it will reach MP. You know that if you are using an ISMB 600 beam, let's say, for example, it will reach a certain MP value. So the question now is, if I want to design the connections, what will I design it for? Will I design it for the demand that is coming through load combinations, 1.5 dead load plus live load plus earthquake? Or will I design it for with the intention that if it reaches MP, which is the plastic moment capacity, which is my intention as the peak maximum that can happen to that beam is reaching MP. Beyond that, it will not attain any force. So I will design my connection for that MP. I'll add a factor because I don't want my connection to have the same strength as my beam. I will put some 20% factor, 1.2 times of MP, and I'll design my connection so that there is a hierarchy always. I mean, if I say it in this way, ma'am, ki if I want my strength, if I want to in a moment frame, if I want to keep a strength, the beam will be the weakest, which is the most ductile element where I want my plastic hinge. Then I want my column to be the second in line and my connection to be the strongest. Whereas in ductility, I count the other way around. I am not expecting any yielding or anything my connection. So the more less ductile can be the least ductile can be the connection, then the column. And because my beam dissipates the energy, it has to have the adequate amount of plastic capacity. So it has to be most ductile. So the same way happens if I have a brace, I will first look at out of beam, column, and brace, my hero is the brace. So my most ductile should be the brace. So I will design the brace first. The peak value that comes from the brace, I'll consider strain hardening, I'll consider material uncertainty. I'll find out the maximum that the brace can transfer. I'll design the connection at the end of the brace for that. And that way I'll proceed from the beam then to the column.
Okay, sir. Fine, sir. Dear participants, if you have any queries, you can just unmute and ask your queries.
If you have huge number of interconnected buildings, means we can avoid. I mean, the efficiency will be increasing. So there is a question is
interconnected in the sense if they are casted, I mean, together. Like if they're monolithically cast, yes, it increases the redundancy. But the question is key. If I would have let's say a 40-meter long building is there, would I be happy to construct it as a 40-meter long, or would I reduce it to 220-meter long building? The question comes into that picture. Like if I have 40-meter long, then the inertia is more, but redundancy is more. If I make 20-meter, then the redundancy is less, but the mass is like now reduced. The forces are less. So it all depends. I mean, in terms of how you want to do, but interconnected building obviously is better. If the geometry is same and everything, it increases the redundancy.
Also, we have seen a damp. They will have a ball in the center of a building which oscillates.
That is tune mass damper. Normally in tall buildings, to cater for these wind, etc., they keep these tune mass dampers. Taipei 101 that they use. That is another way of damping device, which is like again increasing that inherent damping from 5 to a higher value, so that if it vibrates, it dampens out that vibration, so that the people don't feel that acceleration or sensation of being like in a moving building or something like that. Yeah. I think if participants are, I mean, if they want to send questions, etc., it's like 7:30 now. I mean, they can send it to my email ID also. Like if you can collect it and send it also, that is also fine.
Sure, sir. Sure.
Yeah. Right.
From Gauri, ma'am.
Sir, so we can.
Thank you, ma'am.
Thank you, sir. Thank you so much for the very informative session, sir. Like we were able to understand the real scenario, what is happening in the structure, and where IoT can be inbuilt to monitor the structural systems as such. And thanks for showing us the real-time work what you're doing at the center. Thank you, sir. Thank you so much for the session.
Thank you so much, ma'am, for the opportunity. Thank you, Krishna.
Thank you, sir.
Thank you. Yeah. Bye.
Dear participants, the session number 8 is yet to begin. Siva Chidambaram sir from Senior Principal Scientist from CBRI is yet to join. So we would like to ask you to ask some questions to our resource persons.
Economical loss and environmental loss, that's fine. Now, what are the other, and its impact on the society. That's a very important thing to be covered. So disaster may be like, you can see like earthquakes, it's one of the hazard. Uh, Tsunami is one of the hazard. Uh, Hurricanes, tornadoes, one of the hazard. Landslide is one of the hazard. Forest fire is one of the hazard. And nowadays we are facing a lot of cyclones. That is another one of the hazard. So everything is interconnected. Like if earthquake occurs nearby the seashore, sea areas, like you are in the sea, we can say we can expect tsunami. If earthquake occurs in the hilly regions like Uttarakhand, where I am staying, Himachal regions, where you can expect landslides. Earthquake not only the causes for landslides, even seepage issues, rain issues, but also causes landslide. And because of climatic conditions, we are experiencing this kind of cyclones. So now, as per our manuals, many things like we can see, like we have wind issues, earthquake and floods, earthquake with high, very. These are the different type of zones available. Okay. Okay. Now, so what are the critical infrastructures? Generally, if you discuss about, we are having transportation, so roads, bridges, railway networks, airports. Now, you would have easily heard about during severe rainy seasons or due to some kind of cyclones in Chennai, our airports are actually closed. No, why the airports are closed? Number one, you can't allow the aircraft to fly, take off or landing during this kind of cyclones because of huge wind pressure. Number one. Number two, you can't perfectly land or take off during this. And number one. Number two is during landing and takeoff, your aircraft runway should be very in a proper order. Suppose if you have any water stagnation because of low line, if you think that everything is perfect and somewhere some settlement happened, something happened, then it would have been a very big disaster thing, right? So we have to be very careful. That's why during a rainy season, if any cyclones occur, immediately we will stop all the transportation, mainly roads and railways and airports. Like this three will be even all the ships will be stopped. So I have personally experienced this kind of things during my lifetime. Many times, two, three times I have experienced. I have been to railway station, railway network has been vanished, and we were stranded up in like for more than a day or two. Okay, so this is the kind of, see now power and energy. When any cyclone occurs, the first thing is the government will stop the power because electric short circuits and many other possibilities are there. And you would have seen during the flood times we don't have even power because electrical short circuits and electricity transfer to the humans, it is highly possible, right? Then water supply and sanitation, we used to face this kind of problems frequently during the cyclones or flooding kind of time because the sewage water is just connecting with our water supply lines, and we are facing sanitation issues kind of thing. Communication and IT network, when you don't have, we have advanced AI, etc., etc., etc. thing, but if everything will be vanished if electricity is not there, right? So there is no electricity, there is no chance of communication, IT, internet, anything, nothing, everything becomes zero, including the AI becomes zero. So that's communication, IT network is another one. Healthcare facilities. Obviously, our hospitals are already, we have experienced a lot of hospital failures, such as like because of electricity failures, we are not able to provide oxygen to the patients, and we lost many patients during many cyclones, floodings during many years of December's. Mainly Chennai used to face these kind of issues during December many times. So and now dams and hydraulic structure, because dam collapses, so they used to open the damage. To avoid the damage, they used to open the water once it reaches the heavy, so it will create a flood. And housing in public buildings, no, we are having construction, and first question is like, are we constructing building properly? It's a very big question. We have to answer ourselves, are we doing or not? That's a very big question. So if you're not doing anything properly, like you have to experience lot of damages because of settlement issues. Low-lying area means like, because in many areas people are constructing houses in the low-lying areas, which led the floodwater or rainwater to collect in that particular area and led the building to submerge into it, and we are facing the issues. So these are the common issues we have faced in our lifetime. So in the last 10 years, if you have taken the history of total number of events, many events are connected, interconnected actually. Earthquakes are very rare phenomena. According to me, earthquakes are very rare phenomena. In Uttarakhand, it is a very common phenomenon. For Tamil Nadu, for southern states, it's a rare phenomenon. The thing is but flooding is very common and cyclones are very common in the areas where nearby the seashore areas. Floodings are common everywhere because of other areas flooding and because of opening the dams to safeguard things. So floodings are very common everywhere and cyclones are very common in seashore areas. And then because of that, we are facing a lot of impacts. So critical infrastructure failure. So again, I'm taking example. Because of this Chennai floods, people don't have option to use any other vehicles. And we face a lot of issues like in insurance, we have a lot of insurance coverage, but not flood affected vehicle. When the people faced that issue for the very first time, they were struggling to literally they were struggling to how to address this. So we are not even bothering about insurance for many kind of critical things. So here infrastructure failure is like when you don't have options to, for example, I have no access to roads, bridges, and railway networks. So if it is flooded, then how can we go out to bring the materials and necessary items? Okay, so even for emergency, you can't travel from one place to another. You have to wait until the water drains. Even your aircraft may be ready, but you can't reach the airport. You can't reach the railway station because of your affected regions. Okay, so if a critical infrastructure failures, generally we used to say that in India, road networks and rail networks are the real nerves of our country. If it fails at any point, just imagine a nose is particular area of your body is getting affected or some kind of infection happened. You can't even move freely. You will be completely under arrest. So same thing will happen to our country. If it is not connected properly due to any kind of issues, it may be any hazard. Forget about the hazard and disaster. If anything happens to the bridges, so it is disconnected. You can't reach the opposite side. You can't expect everyone to have a boat in their houses. So many people came up with a lot of small boats to transport people from one place to safest place. So that is happened. So everything is because of our critical infrastructure failure. So your bridges are there, not collapsed. Roads are there, not eroded much. Still, your total area is submerged. Again, it clearly says that your infrastructure is failed in terms of water transportation. So even if you don't have a rainwater drains properly, then that is also a critical infrastructure failure. That also leads to a critical network disconnection. Okay, you can see it's one of the example in United States, United States and northern Mexico and parts of Canada. So during this particular duration, they faced a lot of winter storms. Winter storms are very common there. Even in topmost Himalayas, people facing 6 months, 2 to 3 months, they can't even come out of their houses. They have to be there within the perfect atmosphere. In few regions, people will be asked to migrate from that region to other regions to safeguard them from the winter attack. You can see before February 10, the electricity, after electricity, you can see the networks. Okay. So, so it clearly says that we are not discussing anything very innovative or very critical things, common things like if a winter occurs, snowfall severely occurs, then obviously we are going to lose electricity because in those countries they are having underground drainage system, underground concealed electric supplies, whereas here in India, majority the areas are open to the atmosphere. So in our case, it will be even more disastrous thing. So earthquakes, Himalayan belts, and Gujarat Kutch regions are very common. Cyclones, as I mentioned earlier, heat waves and droughts. Nowadays, we are facing these issues not only in Rajasthan regions, like everywhere. Everywhere, the temperature increased. Okay, everybody knows about global warming. So floods, it's not only wherever you have rivers and wherever even if you don't have river, but you are living next to a rivers kind of thing, you are going to experience floods because of overflooding. The water may come through anywhere. So we experience such kind of thing. Landslides. It's not only Himalayas, Western Ghats. It's about wherever you have hills and there are chances for landslides if you do over construction over the building slopes. And if you have too much of rains and your hill slopes don't have any proper drainages, you can expect landslides. And then tsunami. So as I mentioned, like coastal belts are at risk. So this is one of the rapid urbanization. Like this is one of the another things. Like can see the people are just they are taking construction 3, 9, 13, 14, 8, 20, and 2021. So people are just coming migrating from villages towards city, and because when you are Chennai is flooded. Chennai reached Chengalpattu. That is till Chengalpattu to Chennai. Similarly, if you go to Bangalore is connected to those who know. If you go to Hyderabad, it's like north, east, west, south, everywhere is expanded. Why? People are migrating towards the city. So when they are migrating towards the city, they have to get accommodated. So for that, people are sacrificing many places like lakes, ponds, even small areas has been converted. So you don't have a proper drainage system. Even without the proper drainage system, we are simply occupying the ponds, lakes, many open places. So there is no chances of your water drainage systems. So what will happen? Because the water has to go out, it will find out its own path. It will travel everywhere. Finally, it will reach its destination, irrespective of the infrastructure available in between. It happened during this. Recently, you would have experienced or heard about the cloud burst happened in Uttarakhand. I will try to show some of the videos of that. So that's why, because we are obstructing the rivers, and when rivers are getting obstructed, it will one day get outburst because of overflow. So we have to experience this kind of thing. So exact what is transportation infrastructure failure? You can see this is nothing but Kerala flooding issues. During this Kerala flooding, you can see the entire houses are flooded. Houses are extremely flooded. You can see the houses are submerged. Literally, houses are submerged. So now you can see if you look at the left side, the bridges, the water is up to the bridge level, bridge bottom. So in that circumstance, people will not be allowed to travel over the bridge because it is girder placed over the simple column plane. So there is a chance of overturning such kind of thing, or otherwise, because of lateral force, there is a chance of shifting the girders from that point of contact to the edge side. So we can expect a severe kind of very catastrophic collapse also. So your actually road network is cut, and you can't travel from one place to another even for emergency. Now the flood level is this much. We don't even know if further rain happens, even the flood level goes up, even these areas will be submerged into it. Okay, so what will happen if if any kind of infrastructure are getting affected? You can see simple. If a tree fall over a road network, you can't transport, you can't travel. Okay. During flood times, what will happen? You can see the people are how they are getting affected. Whereas on the right side, you can see the buildings are damaged due to flooding as well as severe rain. Okay, so you may ask me, sir, these are not the regular houses. Yes, of course, yes. It is not. It's a kacha house. It's not even a pakka house. But still, people are affected. People are affected. When you come to the left side of this image, you can see in this image, it's a normal Pakka house. It is flooded, so electrical still electricity is there. You can see it's a very dangerous thing. So if a kid is touching some electrical boxes, he may get shocked because of that. Okay, so we have to be very careful. Yeah. So these are various interesting failures due to various aspects, earthquakes and floodings. This is exactly because of flooding. You can see it's because of flooding. This is so if a flooding happens, old bridges are not made using piles kind of thing. It's a shallow foundation. So that kind of time you can't you can't expect the bridges to survive due to the severe erosion happens, and even the piers will be dislocated. Even small distress in the piers will have a severe obstructions in case of so electricity, obviously, as I mentioned, during flooding and severe wind and cyclones, we are facing these kind of electricity issues. First, we used to do cut the electricity so that people can be saved because of electricity issues. But if your network is completely collapsed like this, you can't even restore it immediately. So the people after cyclone, after flooding, so the issues will be remaining as issues, and we have to wait for the complete restoration. So it may take time also. It is not going to be a day process. It is going to be a huge process. Like we have to wait for a lot more days. Okay. So another thing is like how, because now in India and many places like water pipelines are traveling over drainages, sewage lines. So pipeline outburst is also possible. Pipeline may merge with this drainage waters. We are facing this kind of issues. That is called water supply issues. Then housing, public buildings. So if any, it's not only public buildings. If any building fails, then we are facing a lot of issues. But mainly, if a hospital fails, all the people, those who are going to get affected because of this kind of hazards, is going to get suffer a lot. Number one. Number two, people generally what they will do if any people are getting affected due to earthquakes or any kind of flood, tsunami, anything. So immediately people will be taken to a nearby schools or any open big buildings to accommodate them. Right? In that case, if you have a very big halls and schools networks, if it is failed, again the public building failed, we will be in trouble, right? So everything we have to be keeping under control. Housing in the public buildings are having a different type of criteria, like understand the level of damage to or reuse or can be used directly, or repairing works are required, or just completely collapse to be done. So again, it is with us only. So you have to be very proper in construction as per our Indian standard. Not any standard you can follow, but in India you have to follow Indian standard, so that at least we can safeguard our structure with minimal amount of damages. That is more advisable. So what is resilience? The ability of a system or society exposed to hazards to resist, absorb, accommodate, adapt, to transform, and recover from the effects of a hazard in a timely and efficient manner, including through the preservation and restoration of its essential basic structure and function through risk management. If my building is completely collapsed, there is no point of resilience. If my building is experienced minor damages, but that can be easily restored by me to immediately occupy the house, then my building is actually a resilient building. So that's what we want. We are not constructing all the houses to resist earthquakes completely. Instead, we are expecting our buildings to survive with minimal damages, so that I can able to repair and even I can further improve my performance of my building. So what about the concept, because just one clarification, if anybody covered about resilience, building resilience? Organizers, please, can somebody comment?
Yes, sir. Ashwin sir thought some of the topic related to resilience.
Okay, then I will skip all these things. I will go to some other point.
Okay, sir.
Anybody covered about vulnerability and risk assessment kind of thing?
Sir, not fully, sir. They have covered vulnerability also, they have told.
Okay, fine.
Oh.
Okay, so basically, you should know how to do the vulnerability assessment so that no disaster mitigation is nothing but what, like I'm going to mitigate myself from the any kind of disaster, maybe a earthquake, cyclone, or maybe flood or anything. So for that, we have to do a lot of vulnerability assessment. It may be first we have to collect the data of the building. First, you should know the people, those who are living in your building. You people should have an awareness about the type of building you are. So now, for example, in many places, I have noticed people are constructing nowadays, migrating from masonry structure to RCC blindly. They don't even know why are they shifting from masonry to RCC. They are thinking that RCC is a more safer building. No, it's not like that. Even you can make your masonry building more safer than RCC, and masonry buildings are even more durable than RCC. Okay, so now if you look at any kind of, just go to any normal residential construction or GGR G+1, you can just go and randomly look at any construction. You can see the foundation, the column size is going to be 230 by 230, and plinth beam are going up 230 by 450. As per our seismic design philosophy, strong column, weak beam. Okay, if any earthquake occurs, that building will collapse for sure. Okay, let us go forward. They are constructing the column again, and there is no any reinforcement detailing kind of thing. They are going for till lintel, and lintel they are constructing lintel. Then they are going up to a slab level, and over the lintel they are constructing with brick masonry and then slab. So surprisingly, I asked one of the engineers, like, "Arey, what about the beam?" So the configuration cost is like, say, X rupee. Now, if you are adding beam, it is going to be X plus X. Then I said, like, it is not a moment resistant building. Sir, it is an RCC building. I said, it is not an RCC building. It is neither falls under the category of masonry nor falls under the category of RCC building. So it is a hybrid building, similar to as that of a confined masonry building. To make a confined masonry building, you can easily adopt the concept of confined masonry building. That will save a lot of amount. I don't want any shallow foundations. I don't want any kind of plinth beam. So that's more than sufficient for me to resist any kind of earthquake or settlement. So why I'm spending unnecessary money? So you should know about your building where you are. Suppose if you're going to buy an apartment or any kind of buildings directly from a buyer, you should know what kind of reinforcement they have used, whether it is an RCC or load bearing or hybrid kind of thing. You should know about it. Otherwise, there is no point. Like, I can't even categorize. So first collection of data, and then we got to do a lot of modeling about the buildings, and we got to do detailed vulnerability assessment. These are the various type of methodology to understand about the things. So I'm just skipping it out. Okay. This is rapid visual screening. It's very famous in India, and you can just go and see if you want to do any assessment. You can see the building, collect the data, type of buildings, and basic structural informations like what kind of structural system it is. You can easily identify what kind of structural system it is. So, and then based on the results, we can say like this building, whether it needs a retrofit needs. Either it can be done pre-earthquakes or post-earthquakes or post-disaster or pre-disaster also, it can be done very perfectly, so that we can mitigate. Even if it occurs, we can go for retrofitting strategies. Okay. So these are the typical available in available with our NDMA, so that you can take this chart and you can go and you can collect the data that you have done the collection of data. Okay. So now, first of all, thing is like we have to assess the risk identification, risk classification, risk analysis, risk response tests. So just discuss about construction. Just I think it is not also not required for you. Okay. So now in Josimed, recently people would have heard about Josimed landslides. That's not a landslide; it is actually subsidence. So what's the difference between these two? Because we have discussed about landslides, but it is not landslide, land subsidence. Gradually over the year, Josimed is a very one of the peak area in Himachal, in Uttarakhand, in Himalayas. So that is the point. If you want to go to Badrinath, from there you want to take the road to Badrinath. So during winter time, the Badrinath will be closed, the Mana will be closed. That is the last last village of in that particular boundary regions. So the people will be migrated towards Joshimath. Joshimath is the only place where you can access. Still snowfall is there in Joshimath, but still it is accessible by people. So there they have a chopper strip and everything is available. Not no aircraft kind of thing. Chopper strips are available. Let's say. Okay, so that can be a connecting point for Badrinath and then surrounding regions. In that regions, the huge building constructed over a lot of slopes, and exactly below the slope there's a river. That's a river is going on. Now, if you look at if you just go and have a small overlook in YouTube or somewhere, you can understand how vulnerable it is. Like when you have a hill slopes or any hilly terrains, we are not entitled to construct a mass construction over these regions. Earlier, if you look at any hill slopes, hilly regions, people used to be tribal people used to be there. That is their own that is the place of those people. So okay, from here we are going there and we are constructing a very big houses. Slope is slope. Slope is slope. Whatever you do, slope is slope. So when you do a construction over the slope, we have to go for a pile. There are many because stiffness variation is there. So we are not understanding anything and we are simply constructing a lot of houses in the slopes, even including Ooty, Kodaikanal, Simla. Simla is flooded with now Simla even lost its beauty in terms of no, there is no snowfall. There is reduced. Missouri, many places, many hill stations. We lost the nature. No, fully it was green. Now it is fully with concrete. It becomes a concrete jungle, concrete forest. Now land subsidence because of too much loading, and we are obstructing the natural water drainage path. You are literally obstructing the water drainage path from the topmost peak to the bottommost river. When you obstruct a water, the water critically knows how to travel. Water critically knows how to travel. Just imagine, I'm going to draw. Just imagine you have a slope like this, okay, and this is the we can say this is the river. This is the river area. This is the river area. This is the river, okay, and this is the mountain peak kind of thing like this. And if rainfall occurs, the rainwater should travel and should reach this. If your surface is smooth, it is fine. Otherwise, what will happen? It will travel everywhere. So drainage is important. Now, if I'm constructing a house like this and like this and like this and like this and like this, just imagine I'm constructing a house like this. And you are stopping the water everywhere and you are restricting the water travel. So small regions, small streets, drainage paths will be there, it will travel. But when huge water occurs, it will not. So what will happen? It will try to penetrate into the surface and it will travel under the ground, it will reach the surface. So if it travels like this, it will erode the water, it will erode the soil also. So the total region will be subjected to a small drift. This is you may say this is called landslides. Landslide is complete sudden vanish. Subsidence is gradual, it comes down. So just imagine I'm just relocating this point. This is going to be the top and it is slipped from this point. So the total building will be subjected to this is not only the water source. Even if you make a tunnel, if you are making the tunnel over a hill regions, if it is not properly constructed, if it is not properly, if you are not making the drills properly, it may also trigger a slope. So that is also possible for such kind of subsidence. That is happening many places. Okay. So when we conduct the detailed assessment, we experience crack means 1 mm, 2 mm. No, here the crack means like 1 feet, half a feet. Those things are not cracks, not even cracks. It is even more bigger. Okay. So that in hill slope, we have to be very careful in constructing any building. And if it is a very hill slope, and we should not go for random construction, proper design, and accumulation of too much of load is not at all possible. So you would have seen a lot of building touched with pounding effect. We have seen, but we have literally seen there. We have studied, but literally we have seen there. You can see the crack, you can see the crack. This is the crack I'm talking about. This is one of the typical crack I'm showing it. Okay, so they have done a lot of, if you see the government of Uttarakhand, they have done a lot of study to understand how, what happened and how can we go forward to address all these kind of issues. So the main problem here is like over construction, mass construction in a very restricted regions. So if you ask me like how can I prevent disaster, how can I mitigate the disaster? You can't do any mitigation here because if it is already overloaded. So even people have seen the tensile cracks on the road that critically clearly shows that the area is actually getting subside. So um, so in that case, you have to you have to do only one thing is like proper drainage so that no water can travel below the surface. So it should travel above the surface. So that we have to go for it. Just forwarding all these things. So now disaster mitigation. How can I mitigate disaster? No, other things. Now you should know about your building first. You can see the rebar is corroded. Rebar is severely corroded. You may ask, what is the connection with this and mitigation of disaster? If my building is not adequate or inadequate capacity to resist even a small amount of forces, how can I make my building to more resistance towards these kind of natural hazards? Natural hazard, how it is possible, right? So first of all, you should know about your building, what kind of capacity it is, and what are the already distress levels are there in my building. Otherwise, small wind, small rainwater accumulation is more than sufficient. More than sufficient. Okay, you can see. Actually, in this region, the interesting fact is below this. If so just imagine this particular thing is piled below. This is the first floor. This is the ground floor. If somebody is there, it would have fell down over them. So basically, they will die. Okay. If a corrosion is there and if the building roof is fully loaded with rainwater, what will happen? Well, the beam will crack, actually the building will subject to collapse. If your roof slab is having such kind of corrosion and severe water accumulation is happening, means you will experience water dampness, water seepage, and finally collapse of the slab. Okay, so everything is possible. It's not, you have to keep your building safe. So now, how we are not bothering about all the things, like we are letting the growth of vegetation in our building, we are not even bothering about it. Especially if it is public building, we are not even bothering about. Public buildings are more important to be safeguarded for our emergency purposes. But in our case, we are not even bothering about public buildings. Once everything happens, then we are going to do not repair. It's a major repair works. So it has to be properly taken care. We have to do proper repairing works, regular monitoring, regular maintenance. Otherwise, you can't rectify all these kind of issues. A typical example is you can see a person residing in this house is perfectly maintaining his house, whereas this guy is not even bothering about the growth of a tree. Now, if vegetation growth occurs, because of the root growth, the building will experience a lot of cracks like this. You can see like this. In such circumstance, if any small flooding occurs, this is a masonry building. If a small settlement occurs, already the building is weak, so the building will subject to a catastrophic failure during a flood and subsequent settlement issues. So this guy is perfectly maintained, but this fellow is didn't maintain. But it is the collective responsibility of these two guys. So both the guy has to be maintain the building properly, otherwise it will be difficult thing. So it is not like it is mine, it is yours. So when you want to fight with any kind of hazards, so you have to make sure my building is adequate enough to resist those kind of forces. So if your building is in low-lying area, you should know how to lift the building, how to keep your building protected. So now you can see these are the typical observations we have observed in many buildings during our assessment time. So these buildings are already in weak. Now, due to overflooding, due to floodings, what is happening? The buildings are frequently subjected to a water level up to a certain height. So in a year, if it 2, 3 times, 4, 3 times means the water will drain out, but the dampness will accumulate at this particular point, and it will keep it will make your column reinforcement to expose to polluted water polluted regions. It will corrode your reinforcement. Okay. Okay. So, what is the need of disaster mitigation? I have clearly explained that it has to be, we have to mitigate in advance so that we can avoid complete failure of any of our buildings, and we can safeguard our buildings. So now in India, this NDMA has introduced the concept of PDNA, that is called Post Disaster Need Assessment. People should know about it. In this, the concept of reconstruction occurs, because now earlier we got a disaster, now we got affected. Now, what is the need of PDNA? Okay. So, what is the need of PDNA? Is like after complete collapse, like in Kerala, the sudden slide, you would have seen. So how much the devastating disaster happened. So we lost many lives, many houses. And then in Chennai and Pondicherry, huge floodings. I have been personally to visit that particular places. It's a huge disaster, huge damages to the buildings. And now coming to Telangana, there are also huge defects because of flooding. What I'm talking about is flooding and flooding and flooding. Then in Himachal, it is again cloud outburst. In Dehradun, again, it is a cloud outburst. And in Punjab, it is again flooding. So it's like, we are getting affected frequently, but we are not bothering about it. We should know what to do, what not to do, and what to do to go further so that we can completely avoid all these kind of damages. That is the main aim of media. We should learn lessons from the issues, disaster, damages, and how to recover that, and how to coming out of it. The concept is build back better, so that even further earthquake comes, flooding comes, cyclone comes, anything comes, my building is not going to get affected. I will be in safest side. So that is the main aim of PDNA. So that is called post disaster need assessment. Okay. So the thing is like it's our responsibility. If anything happens, first thing will be our development, everything will be stopped. So here is we lost. So we need recovery. How to recover from the situation? Then we need reconstruction, so that I can able to avoid this kind of future issues. So I need post recovery and reconstruction procedures, in which we have a immediate, short term, and long term. These are the concepts. It will be proposed out. Okay. If you have any issues like any flooding, first thing responding team will be your district team. Every district team will have a state-based disaster relief force. And then we have a national disaster relief force. So these people will come and will try to help you. But at the same time, every district headquarter office will have your minimal amount of disaster relief measures. Like they have a boats, they have a lifting tools, climbing up tools, many things. They have all the things, so that only people should know what do we have, how can we approach, how can we approach them. So very interestingly, I will tell you one small story now. During one particular, I don't want to mention the state and place. In one particular place, due to flooding, they have a rainwater monitoring system. That monitoring system has been completely flushed away due to severe flooding. Before the signal reaches the district monitoring place, it vanished away. So they don't even know whether the flooding is happening or not. So without realizing that the time span is very less, the meantime, it is completely vanished. So severe flooding occurred. So they informed the people. So the people, what they said is, you people came few months before, you said like, evacuate, flooding, nothing happened. And now you are again asking, evacuate, nothing is going to happen. And they have taken it very lightly. No, in fraction of time, the flood happened, so people affected. So, district office reacted fast, but people didn't react fast. So finally, they suffered a lot. And then the very interesting thing is when everything is happening, people are getting migrated. Nowadays, the trends are like taking the video and circulating in social media kind of thing. So one set of family is getting affected, stranded in a house. So everybody is taking the video, even including the media, focusing and focusing and focusing and focusing. That is few people. Majority of the people are getting stranded now because of the media pressure and public pressure. Everything has been towards them, and many people are getting affected. So it is a collective response. It's not a single government will come and take the response. It is a collective response. Even a small support to the government or a small support of government. So it's like mutual thing. So we have to be responsible in every aspect. Okay. So basically, PDNA will focus on all aspects. What is the loss in agriculture, financial loss, industrial loss, tourism loss, housing, education, health, culture, water, community, energy, transport, everything will be counted. Everything will be counted. Immediate relief will be provided. And for future schemes, how can we go forward? Now, we have masonry buildings, RCC buildings, steel buildings. Still, we have mud houses, kacha houses, normal pitch-proof mud houses are still there in many parts of our country. We are looking at very well-developed cities, but we are not bothering about underdeveloped, poorly developed areas. Those people are easily getting affected. One more issues nowadays we are facing is like the highways. After highways, if you look at the highways, both left and right side of the highways are literally low, and water will not travel from this side to that side. We don't have proper drainage systems, So that is also getting affected. So all these things will be covered by our post-disaster need assessment team. So they will thoroughly examine every aspects. They will go to the place, they will talk to the people, they will count the losses, economic losses, and what are the recovery needs you want. So this BBB is nothing but build back better. Okay, build back better. So what is build back better? So first we will these are the recovery strategy we will provide, and financial resources. Whatever the financial resources we can able to avail from the government can be provided. Plus you have to invest so that it can be a cumulative outcome. So first we have to talk about damage. As a building damage, my car is damaged. Okay, this all comes under the category of damage. Loss. I have a financial loss due to because I'm not able to go to job. I'm not able to go to do my business. So I'm not able to transport all my goods to some other places. So these are the losses regarding the financial. And another loss is like because of over flooding and flooding into my houses, I lost my properties, I lost my materials, I lost my assets, everything. Okay. And its effect is like if I don't have a salary for a month, what will be my effect? That is the post effects. And its impact. Obviously, we will have a lot of impacts because of I don't have money, because of sanitation, I'm going to have medical issues. So it is like a continue process, and needs will be, we will have a lot of needs. So people, if you go there, first people will surround you and they will ask, I need this, I need this, and how can we provide? How can we provide? That is our task. Like, so we have to do all the support to the people, and in which way we are going to do. That is the needs actually. So let me skip all these things. So just imagine a typical example is taxi guy will lost his income because the taxi movement is stopped. Building houses lost income from rent because my building is submerged. Airport structure because lost income because of what? Airport is not optioning. Roads and bridges, construction of temporary bridges needs a lot of money. That is a loss. Hospital building and equipment is lost. That is a loss. Okay. So damage is asset based and losses based is like our financial losses, material losses, etc. will be covered. People should know the difference between these two. Okay. So priority of recovery is short-term needs for immediately. What should I do? What should I do? So I have to relocate the people, and I have to make temporary bridges. I have to provide proper drinking water. I have to accommodate people with proper shelters, and I have to provide a minimal amount for their immediate support, medical teams. And medium term is we have to immediately reconstruct their houses, repair works to be done, and we have to move the people, clean the area. And long term needs is further in future, this kind of problem should not come. For that purpose, we have to improve our infrastructure. How can we improve that? That is the long-term needs. Okay, reconstruction, resumption, restoration of and risk reduction, reconstruction of infrastructure and physical assets. It's not a simple thing. Reconstruction of bridges. So what is the need of reconstruction of bridges? If you think like my bridges is actually old bridges and still it is surviving, but in future it may not survive. So what we have to do is that has to be reconstructed with new bridges of new advanced technology so that I can completely avoid erosion of my piers and subsequent failures. Okay, and then I can avoid further erosion, and I can at least control my disconnection of my transport facilities and drainage systems. I have to reconstruct with the amount of volume of water, because earlier we had 10 lakh people, now we have 15 lakh people in a particular city. So 10 lakh water discharge, 50 lakh water discharge. Just imagine. And area is same, but people are increased. So construction of volume is increased. So the water and everything need is very high, at the same time, drainage systems are the same level. So that has to be reconstructed so that I can easily drain the water if a small rain occurs. And the very importantly is like railway networks. Now we have in metros. If you look at metros, many of the metros are bridges, and few of them are traveling under underground tunnels. So if you have just if your railway systems are elevated, then once the rain overs, then I can easily transport my things. During very interestingly, if electric train is during this cyclones, floods, immediately electricity will be turned off. So electric train can't run. So how people will? So immediately, railway network will deploy one diesel-based engine immediately. Even I have experienced such kind of situation once in my life. So they have transported the train coaches to a nearby railway stations, like where it is like completely safest region. From there, electric engine came and it took off. So these are the alternative arrangements. But to avoid this, reconstruction is like, if electrical problem occurred, they got to stop. So they got to provide an electrical system so that I can able to make my transportation without any effect. So bridges, houses, and road networks, and my public buildings to be perfectly reconstructed so that I can able to avoid all these issues. So elevation is very important when you go for reconstruction, and height of the building is very important, so that if your building is located in a low-lying area, it is your mistake. You have constructed a building in a low-lying area, or you bought an apartment in a low-lying area. Finally, we should not blame the flood. Flood will come and correct in a low-lying area only. So it is our duty to construct a building to elevated height so that I can able to prevent my houses from any kind of flooding. That otherwise I can able to safeguard my building. That is our ultimate target. It should be an ultimate target. Reconstruction of infrastructure and physical assets. It's like value of damage and plus cost of improvement plus technological modernization, relocations when needed, plus disaster resilient features, plus multi-annual inflation. So see, the very important is very important thing is like when you go for new construction, we should not go blindly. We should not go for a blindly normal reconstruction process. When you go for embankment, for example, I'm talking about this water canal linings. When you go for if any breaching occurred in the canal lining, we should not go for again just again fill with some kind of soil. We have to go for improved technology. See what do we have now? Right now we have a geotextiles, geomembranes, geoshells to improve the stability of your any kind of soil embankments. So that is called technological modernization. I'm going to refill the area, but with technological modernization, so that I'm not going to erode. Suppose some rivers are there. So rivers are having some curves. So if possible, I have to remove those kind of curves so it can travel smoothly. That is kind of support we can provide. And many times we experience like the people located near the shore areas, so they are getting affected. So riverbed areas getting affected. Why people are located to the next to the shore area, riverbed area? Because of their business, or some people don't have space, so they are residing next to that. So there's those people to be relocated properly to a proper area. So where construction to be done, their construction to be done. Where construction should not be done, their construction should not be done. Example is very simple example. Every district will have a industrial area. In industrial area, no construction is allowed. But people will go there, they will construct small things, shops, and subsequent houses, and everything after completing a colony, then people will start to protest. We are facing a lot of pollution because of this industry. Kindly vacate the industry. That is actually an industrial area. We should not go into it. But still, people are going, establishing the colony and protesting against the same industrial area. So it should not happen. No, where you should not do construction, you should not do. First, know about your area and do the construction. Okay, and basically supports. If you have a build back better concept, you have to do a proper construction with the proper mitigating measures, so that I can able to avoid all this kind of stuff. So I have to relocate myself to another area. Government will provide you the land. Government will provide you the land. You may ask me, sir, government will not provide you. Yeah, we have seen government is providing. If you have losses during this flooding time in an area, if the land belongs to you, so they will give you some other locations in some other area. Of course, you will feel like distinct, but there is no option. We got to go away from those regions, so that I can able to avoid myself in future course of action. So when you go for disaster risk reduction, I want to reduce my risk and during any kind of floods or any kind of thing. So I want to elevate my floor level to a higher height. Now what is happening? We are constructing a road, over that another road, over that another road. Basically, it should not be. We have to remove the boulders and we have to reconstruct so that the road level remains same, but we are not doing that. Are we taking any action against when the increasing road level? No. Because of that, our buildings are going down. Very 25, 30 years old building, you can see the road levels went up and buildings went down. So basically, road level should not go up. But we are constructing a road over another, over another, over another. And because of the road level is going up. So now when you talk about build back better, so you have to increase the height of the building to at least 1 meter height, so that in at least next 30 to 40 years, my road level will come to that area, so it will be fine. Okay. So everything we have to consider. And these are the different recovery needs. Let me show. Yeah. See, this is one of the observations. Now, this two building you can see, you may say, sir, these are all mud buildings. These are all mud buildings. People are still living in this kind of building. Number one. Number two, this building, this small building is located in, this is the road. And this is actually a pond. Actually a pond. You may ask me, sir, these are all mud. Of course, yes, people are living there. So if you ask them, please vacate, they will say, where to go? This is my building. This is my house. This is my life. This is my street. Where to go? So these areas were actually flooded during flooding. So one of the building is completely collapsed like this. So now what we have to do is people living in these houses, low-lying areas need to be relocated to avoid this kind of flooring. So relocation is must. So the people below the poverty are struggling to make the use of government schemes for construction of houses due to inadequate initial fund up to foundation. So they have limitations. So government should come up with some alternative methods so that foundation will be provided by some other agencies. So it can be funded by government. So flood resistant structure. So that if my buildings are low lying area, I need a protecting wall so that I can avoid these kind of problems. So houses affected due to inundation needs be considered for relief in addition to the damage relief fund. So when you do post disaster need assessment, we will know what are the need of the people so that we can easily come up with some beautiful solution so that we can completely support them in terms of reconstruction, in terms of supporting to improve their habitat. Okay. And so now you have a lot of AI tools. Now we have used in Josimed, we have used drones to map the areas. And with the help of satellite imaging, we know the earlier affected thing and post-affected supports, and where the buildings are severely damaged. Now, satellite imaging will be from the top. Now we have drone imaging. Drone imaging helps you so that I can able to close by to the houses to see the type of damage, the level of damage. The beautiful is now we have mounted a lot of sensor with our drones, so that even if I touch my building portions, I can able to identify what kind of, by through and capture the image. Now I'm using a lot of advanced algorithms to identify what type of cracks it is, and what is the width of the crack. So if it is a 4-story building and I'm standing in the ground, I can't climb up because the building is damaged. Now how can I go to the top to understand what type of damage it is? I'm using the drones I'm taking the drone to the topmost floor, and it is capturing the image, and it gives me not as an image, as an interpretation, like this building is having a fluctual cracks, shear cracks of width this much, and we have observed corrosion strains and corrosion of rebars, volumetric expansion. Everything can be now we have done in with the help of AI, and they have made algorithms, and now the tools are available very effectively to give a overview about the building damage with the help of these kind of tools. Okay. So this is the different type of PDNA manual. So you can look at the manual. So it will give you a wonderful outcome, and you can see everything is free of cost. So when you look at those data of different states, it is open to all, so that you can understand how the disaster can be mitigated, how the disaster affected, how the reconstruction and recovery needs has been proposed, how can people survived, how did they survive, and how can we improve. Everything has been clearly given, and including the schemes provided by the governments. So these are the typical schemes. So finally, the community preparedness, infrastructure assessment, temporary diversions, traffic restorations, early morning improvements, debris clearance, everything we have to focus, so that we can go for we can mitigate ourselves from the disasters, and even if it occurs, we can bounce back very immediately, so that we can address any kind of issues. Just a minute. So quickly, I will go through this reconstruction process. Okay, so one is like restore. First, we have to already have covered many things, and pre-request, like we have to assess the damage, and we have to collaborate with the stakeholders, and resource mobilization, and emergency response planning and design, and infrastructure reconstruction. So for damage assessment, we have to use any one tool like rapid visual screening, and many other tools are there. And whether it is repairable or just we have to collapse and reconstruct it. Now you have to collaborate with your stakeholders, so that with the help of non-profit organizations, government will fund you, So how can we take with the collaborate with stakeholders so that I can able to go for better construction and resource mobilization, like no secure funding. Now we have getting a lot of loans with a lot of supportive reduced interest. So how to funding that? So in future, when you go for a proper planning, considering the seismic resilience. So when you consider seismic resilience, wind is also considered. So flood is also considered. But tsunamis are not considered, because for tsunami, it is a different type of procedure we have to follow. So according to the need, it has to be considered. So timeline of when the disaster event happened, then we got to go for immediately relief phase, that is the first phase. Then recovery phase, we got to allow the time to recover. Then the reconstruction phase. When you go to reconstruction phase, we have to go with the concept of build back better. That is the concept of PDNA, so that I can able to make a sustainable society, so that I can make my people for future preparedness, and I can be more even strong, that nothing is going to happen to my buildings, or my I'm not going to have a much loss because of this. Okay, so we have to be we have to travel from this point towards this point. Okay, so it is the main task of post disaster need assessment. So what is build back better? So as I mentioned in many slides, when you affected by a disaster, when you are coming back from the disaster affected or disaster impact, when you are making your building, if you are low-lying area, you are elevating your things. If your building is, your bridges are very old, you're going to reconstruct with the new bridges. If your roads are getting eroded because of erosion, rainwater erosion, you are going for rigid pavement instead of a flexible pavement. And if your electricity is getting affected, going for underground thing. If your drainage system is not adequate, go with a very big drainage systems. So we have to go with a proper methodology, so that nothing is going to happen to me in future. So that is my ultimate aim. That is the concept of build back better. So what is the role of civil engineer in this case? In this case, is like everything is related to civil, right? So damage assessment I got to do. Design of disaster resilient infrastructure, civil engineer roles. Retrofitting and strengthening of existing building, using a durable and a very cost-effective solution to be done, and quality control, because now in India, most of the structure are getting affected because of one major thing is called quality control. We have studied about this in books, but we are not following in practice. Because of this, we are losing a lot of funding, lot of resources, materials, money, everything is getting lost. You would have heard about my building is getting corroded, my building is piling, kind of thing. So those things are why it is happening, because of poor quality control. Those things should not happen. So government has a lot of schemes. These are the schemes examples I'm showing you. It's available in online. You can take it from anywhere. So with the help of this, additional amounts can be made up and we can make a good buildings. Okay, I'm not going to much about this because these are all funding schemes. Yeah, so I'm just stopping my presentation here. So we can keep our platform open for any questions. We can have a discussion. Anything else we can discuss now?
So thank you, sir. It was really very nice presentation, like giving us an overview about the vulnerability assessment and how the practical things are working on. But like I have a question, like in India being a dynamic country, like how do we get the things done so that the disaster mitigation measures are being monitored each and every time, so that we can focus on how the risk can be controlled. Like at times we cannot prevent the risk happening and encountering the risk, but how do we get the measures being done effectively?
Ma'am, India is a very vast country. We have earthquakes in northern Rome and in Gujarat regions, and flooding everywhere, and like rain cyclones in seashore areas. Now, every region has its own defined hazard levels. Like for example, if you talk about Tamil Nadu, they have hazard levels. Don't bother about earthquakes. because it is not going to happen, or very limited sources are there.
Yes, sir.
If I'm talking about Uttarakhand, hazard level is earthquake is predominant, landslide is predominant, flooding is predominant. These three phenomena is every year phenomena. So I'm located at Uttarakhand. Here landslides are very common, and flooding is very common. Cloud outburst is nowadays getting very common. Like yearly once gone, now yearly twice or thrice are we are facing. So now this defines the hazard level. So now if I want to construct a building, I have to make sure my building should able to resist earthquake, landslides, and floodings kind of thing. Now, if you take the concept of landslides, I should not construct exactly in the hill slopes. If I'm doing construction, I should do construction in a film soil. If it is not there, I got to go for a pile. If it is a mass area is getting slided, you can't do anything. So whether that particular place is suitable for construction of houses or not, any kind of buildings or not, that we have to ensure. So for India, we have state. Every state has multiple districts. Every district has its own hazard level and disaster risk reduction protocols. So you should know about. That's what I'm telling you. Every district headquarter has all the disaster need. Okay, now for example, I'm telling you, in Tamil Nadu, I have been in the last year for this PDNA work. So they have a wonderful monitoring system from the headquarter. They can able to see which person has electrical equipment, which person has welding equipment. So for emergency, they can approach. Such kind of advancement they have now. So you should know about your own place, and if you know your hazard level, then you can make your construction in a very proper way. We can address, at least we can resist these kind of issues. We can make our building more resilience.
Dear participants, like, if you have any queries, you can just unmute and ask the queries.
Sir, sir, it was a very good presentation, sir.
Thank you.
Many pictorial views you have shown that is very perfect to understand much better way. And I have a very important question, sir. That is sustainable development goals. So we used to read this everywhere, and this is being affected highly due to disaster. And my view is whether in the recent days we can see there are many flood occurring in Tamil Nadu particularly, and we are not marching towards the goals. Even if we are marching to the goal, the disasters coming and affecting the goal. Am I right, sir, or is it the correct way to go?
See, it is a policy based. Many things are policy based. That's why I mentioned, many people are migrating from small villages and towns towards a particular place. So let us assume it is Chennai. It is overpopulated. When you are overpopulated, you have to go and occupy the a lot of ponds, lakes has been converted into apartments and constructions. Now, where the rainwater will go and actually get stored. Number one. Number two, there were a lot of rivers. Now it is not rivers nowadays. It becomes a sewage and drainage kind of things. It was actually, it was river. It is not a drainage kind. So now the river wide, it becomes short. In many places we have seen the river width is this much and now current width is this much. Everywhere it is occupied. So when you are restricting the nature, you are completely restricting. See, in your heart, blood vessels have some small blocks. Heart attack is coming. The person is dying. Same thing if you obstruct your rainwater pipe, rainwater system, rainwater systems. It is like a heart attack for the city, heart attack for the locations. So obviously it will overflow and you will be submerged. So it is now our duty to make the construction proper. Now construction is secondary. First you should identify how the water will come and how can I drain the water and how can I make my area free from, or I have to keep my area clean during this flooding time means I have to drain my water. So it is like it's not a simple solution by you or me. It's a completely policy thing. If you properly plan restructuring your city drainage system and rainwater draining system, this can be easily addressed. This can be easily addressed. And simple thing, if you are in low, Chennai is flooded, whereas Madurai is not even flooded. There is no chance of water. Now, do we have any option to connect this water to there? That is a policy level making. If my overflooding is there, I need to pump out the water. You may ask me, sir, it is not a possible thing. It is possible. If you know how to do that, you can shift the water from this place to another place where there is no water at all. You can save the water. So at least you can, of course, it's a very huge investment. If you properly make it, we can achieve that.
Participants, if you have any questions, you can ask now or you can post in the chat box. Okay. Ma'am, I think there is no questions.
Sir, thank you very much, sir. It was really
The
indeed.
power of.
It's okay, sir. It's okay. Thank you for giving your immediate response to give a talk in our ATAL FDP sponsored FDP. It was very informative and things that are actually happening. We were able to capture that through the pictures that you have showed us, and this is a different perspective with which we have to look into this. But as you said, the policy things might come into picture, something that might not happen in our hands. But still, as a citizen, we have to move into reducing the vulnerability. That might be our part. Thank you, sir. Thank you for giving your valuable time with us.
Thank you, ma'am. Thank you for inviting me, and I thank all the participants because it's like almost like we are closing to towards dinner time. So I should not. I don't want to be between the dinner and this session. So I thank all the participants for your patience in design. If you have any queries, any questions, feel free to contact me. My mail IDs are available in internet itself. You can find it. Huh? I thank the organization for inviting me and particularly for this session. Thank you so much.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
This meeting is being recorded.
ஆமா சார் தெரியாது ஆமா சார் தெரியல தான் சொன்னாங்க ஓகே சார் ஓகே சார் ஓகே சார் அனுப்பிச்சுடுறேன் சார் நான் ஓகே சார் You're not with tonight.